Good morning. Good morning, good afternoon, good evening. It's now 11 o'clock and we're ready to start day 2 of this wonderful conference, Engineered Bamboo for Sustainable Development, with the University of British Columbia, the World Bamboo Organization, and some wonderful sponsors. I'm going to do a little bit of housekeeping first. My name's Suzanne Lucas. I'm the executive director of the World Bamboo Organization, and we've got a great program again today. Yesterday was fantastic, and if you were with us, thank you for joining us. And if you weren't with us, we will be sharing the recordings at a later date. We'll keep you informed. I'd like to introduce very quickly Chungping Dai, who's been the organizer of this event from the University of British Columbia. Would you like to say anything, Chungping?
Yes, thank you, Suzanne. And just welcome everybody. I'll be the first speaker.
Yes, thank you. I'd like to introduce our co-host, Dr. Shirla Sastry. First of all, he's a great friend of mine, and I'm happy to say that. But I'm going to give you a little background on Dr. Sastry because he's had quite an illustrious career, very relevant to the topic of this conference. He was born in India and came to Canada as a graduate student in the 1960s. He holds an MS in forestry and a PhD in forest products from the University of British Columbia, Master's of Science and a Bachelor of Science in Honors in Botany, Bachelor of Science in Biology from Andhra University in India. Dr. Sastry joined the International Development Research Center of Canada in 1983 to conceive, develop, and administer the IDRC's forestry, environment, and natural resources programs in Asia and South Pacific. In 1993, Sastry developed the Bamboo and Rattan Network into a formal operation linking governments, NGOs, and research institutions around the region, based in New Delhi. He raised millions of dollars for its operations and created the organization as an IDRC special program in 1994. In November 1997, he was appointed the founding Director General of the newly created International Network for Bamboo and Rattan, and an independent international organization established through treaty and headquartered in Beijing, People's Republic, China. He is lovingly known as the father of INBAR. Excuse me for having to read this, but I don't want to miss any of the great details. He retired from service at the end of 1999, and in September of 2000, he was appointed as an adjunct professor of forestry and an associate of the Institute for Environmental Studies at the University of Toronto in 1990. The Chinese Academy of Forestry awarded him the title of Honorary Research Professor for his outstanding contributions to the development of forestry research in China. The chairman and the board of directors of INBAR in January 2000 conferred on Sastry the honorary title Distinguished Fellow of INBAR for Life in recognition of his outstanding service and contribution to the organization and its aim. Dr. Sastry has authored or co-authored over 50 scientific and technical publications and books in forestry, forest product, and agroforestry, and lectured at several national and international workshops and conventions. And he was awarded the World Bamboo Pioneer Award by the World Bamboo Organization. It's our pleasure to have Dr. Sastry as co-chair today.
Thank you very much, Suzanne. I feel old. I remember, we have come a long way, especially UBC. I remember my first seminar as a grad student is on bamboo, 1965. None of my colleagues know what's bamboo because they're all Douglas fir, pine, and all that. And then we have come a long way since then. 1979, you call me father of bamboo. I would call Walter Lise the grandfather of bamboo. He's the one who introduced to IDRC and me the value of bamboo and the billion people that depend on bamboo. So 79, 80, IDRC created, called the first meeting of experts and local scientists in Singapore. And then we have not looked that back, but since then, IDRC poured in close to $20 million from roughly 1980. Since I joined 1983, the whole program expanded, including Rattan. And Dransfield is another expert who helped us. Many others, Jules Jensen, Charlie Youngie, many others. At the time, there was no, it was the only IDRC bamboo rattan network. So we managed to create an international intergovernmental organization in 1997. I'm grateful to China, who offered to host it, and built a huge palace eventually. I call it palace because it is the biggest bamboo rattan research in the world, in the hosting that. Since then, they have taken over, and I'm very happy to see it flourish. And now it's one of the key sponsors of this, along with World Bamboo and the UBC. Again, thanks UBC. We started modestly, but now look at that. You're organizing a World Bamboo Congress, kind of with close to 1,000, 1,500 people participating. It's a very, I'm very impressed and I'm very grateful, for people like you who are equally good, because we started an intergovernmental organization, but you did start from a international, what were they, with the predecessor to WBO?
International Bamboo Association.
Right, and now, no, you're much bigger than INBAR, I would say.
No.
Because, you have more countries. INBAR has about 54 or so. Now we have how many countries? Maybe 80,
Mhm.
And also the kind of papers I've seen yesterday, my God, fantastic.
Mhm.
I think, 2 billion people rely on bamboo, and it's the right thing to do. Promote bamboo, not only in developing countries, but also here in Europe and North America, Australia, because, that's one way, to address the environmental issues as well as the economic issues. And then preserve our forest, for carbon dioxide and whatever,
Yeah.
So thank you again. I'm happy to be part of, co-hosting this along with you. I'll ask you to take the lead. I'm getting old at 85. I'm still in one piece. Thanks.
Okay. Well, thank you again for being here. Today is about research. Where our topic is research, and we've got 6 speakers. We've got a lot to cover. I just want to remind all the participants that we are using the Q&A function. You can post your question on the Q&A. You can use the thumbs up to advance the question if you agree with the question and think it's a valid question, and we will try to get to all of your questions either after each speaker or during the panelist session. So our first speaker, and I'm happy to introduce Chungping Dai. I just recently introduced him, but he is going to be speaking on engineered bamboo processing routes towards sustainable building application. He currently teaches and leads the research program in wood and bamboo composites at the Department of Wood Sciences, UBC, and he will share his research with us today. Thank you, Chungping. The floor is yours, Chungping.
Yeah, sorry again. Yesterday we had a wonderful session about product and application. Today we're going to focus on the research side. Particularly for my talk, I want to talk about the manufacturing aspect of the product. There's been a lot of discussion yesterday about the cost and the gluing and the properties and so on and so forth. And then I think there's a lot to be studied and understand before we actually begin to develop technologies, and that's one of the goals for my group at UBC. And I'm very proud to present the group of young enthusiastic professionals and students and visiting scholars as well. And they're embarking on various aspects of bamboo product processing, and most of them are here today. So I'm not going to go through all the details of what they do, but without their hard work and support, I wouldn't be here today to talk about much. And the first thing that I want to talk about is coming from my background, coming from the wood composite and wood product. And I like to see the engineered bamboo composites, just to compare that with the wood composites for two reasons. One is the wood composites, in my view, is much more advanced. And then secondly, there's a lot to learn from the wood composite, and in the end, the market for bamboo, engineered bamboo product for particularly in building application is going to be end up as a complement to existing wood products. So I'm going to talk about 6 major topics, and firstly talk about the property resource aspect, and then drawing, gluing, forming, pressing, and then we'll talk about also the conversion pathways. And first of all, the bamboo properties. If you look at the cross section of a bamboo, the density vary significantly, and also the property changes very much as well. Mainly the outer skin area is much stronger than the inner skin area, just because of the fiber content concentrated around the outer skin area, gradually decreasing toward the inner core. So if you look at the fiber of bamboo itself, and the strength is very high, and the bulk of the fiber bamboo upon bamboo wool actually approaching the mild steel, carbon steels. And so there's lots of potential in terms of what bamboo can offer as a material complementing wood. Again, if you compare the wood properties, and then you can see the variation in density, and then particularly the MOE for bamboo is slightly lower than equivalent of softwood that's commonly used for construction, but the strength is much higher. And so there's a natural advantages for bamboo when it comes to using the material for the construction application. So if we one of the approaches we've been looking at is to combine bamboo and wood, and if you add wood to bamboo, and then naturally you can probably reduce the density, but at the same time also improve the modulus of the elasticity. And on the other hand, the bamboo is harder and the strength is higher, so the material will be harder, and also the strength will be also improved. So we're mainly looking, as we move along, looking through 3 types of product: the panel, the lumber, and the mass timber type of products. And one of the attributes about bamboo is that bamboo has a very hard skin, and the skin contains a lot of wax and silicas, and that makes it very difficult to penetrate when it comes to glue application. And also if you look at the structure of bamboo, the cross-cellular permeation is very low, because the pitch is much smaller in bamboo than wood. That actually bring up two major problems. One is the gluing, the other is the drying. So we talk about drying first. Drying current as the way it is currently, there's a lot of steps, mainly 4 steps to go through as part of the treatment process as well. As we know in the next slide, we'll talk about in the next slide that the bamboo has a lot of starch in it, so that treatment is a must for bamboo product, and to avoid mold and decay. And then therefore you have to combine the drying as a process of the treatment. So it's a very lengthy process. And here's a look at some of Monica's, Xia's work. She's doing a master's thesis on how to dry bamboo and how to actually treat bamboo and improve the property by removing some of the starch. And because of the starch, because the inability to withstand the weather, as we do see in wood products, and for bamboo, a lot of bamboo has to be processed when they fall right away, almost within 2 weeks, otherwise it will go mold. And so the first action will be actually to treat it and dry it. And there's a lot of way of processing the product, but one of the way we're thinking is that you process the laminas first and then treat it in a remote area that close to the resource, and then you can center the lamina and then even export it for lamination with wood and making the final product close to the market. Switching the subject a little bit, most of the fundamentals of bamboo composite, whether it's pressing, forming, and gluing, is very much similar to wood composites. And so we've done over the years much work to understand the structure and the property and the various manufacturing behavior of wood composites, and the tool that we developed, such as a computer simulation, can be readily applied to understand how, for example, bamboo scrimber is formed. So if we look at how the bamboo scrimber is formed, and if you look at the thickness of the product and the thickness of the scrimber itself, the piece of the bamboo is just too thick, and it causes a lot of variation. And also in doing the preparation of the bamboo strips, and there's a lot of internal cracks that take place and that need to be filled with resins. That was the main reason that the resin content has to be so high. So this is one of the processing area that we think there's potential to improve. The other area, if you look at how bamboo is consolidated, and how it has to be brought together to a solid product, and if you compare that with wood, and then there's very little compression can occur if you compare the high densification of wood in the same piece of hybrid product, and so if you look at the general relationship of the goal of pressing, that is to bring pieces of these, whether it's bamboo or wood, together to create intimate contact. And with increased density, of course, you will have an increment of contact, but because the natural density of bamboo itself, it takes much greater pressure and densification to create a significant bonding. And if you look at the pressing itself, there's a lot of consideration to be given to the moisture aspect, and because and there's moisture in wood as in bamboo, as well as moisture in resin, and those moisture under high temperature and pressure condition can create a lot of pressure and steam pressure that can cause blows or delamination. So that has to be managed very well. That, in fact, is one of the key issues that we try to understand what's happening in terms of pressing of high density product like bamboo scrimber. So it's the same principle as you would see in how the temperature changes in wood composites, how moisture move, how the internal gas pressure generated, as well as the deformation changes. And with that, we figure that the current way of pressing scrimber, for example, is highly inefficient compared to how we're processing wood products, and it just takes too long, too inefficient, and then just because you have to cool it down and you have to heat it again. So there's lots of potential there to improve upon on the efficiency and energy use as well as productivity. And one of the major aspects that also differentiate between bamboo and wood composite is the bonding. And bamboo is harder, and so it provides a greater potential for higher strengths. But on the other hand, bamboo is harder because, as we mentioned earlier, there's a inability to penetrate resin. Therefore, there's a problem of creating the durability aspect, and which is currently measured by the failure percentage of the fiber, whether it's wood or bamboo. So if you look at especially when the product is wet, and the percentage of the bamboo or wood failure is very low, and that can signal the problem of a durability issue. And this is, in fact, a very essential aspect for wood or engineered wood product, and as stipulated by current standards, whether it's glue laminated product or panel type of product, the bonding is not only evaluated by the strength itself, but also the durability, where the sample are subjected to various accelerated weathering conditions such as moisture and heat. And then you pour the sample, you open it, and you look at how much it fails in wood, how much it fails in glue. So same thing happened in bamboo. We expected for bamboo product to be a suspect that has to be looked at it seriously to improve the failure percentage of bamboo fiber. And one of the strategies to deal with that is to manipulate the the molecular weight distribution of resin, and even combining that with wood, it actually helps to improve the durability. And just switching the subject a little bit as we move toward the end here, is just we have done some review on current way of manufacturing various bamboo-based product. And we talked a lot about bamboo scrimber. As a matter of fact, if you look at the major two products right now is basically it's a laminated bamboo product that can be cut and stripped tangentially, and making the strips, and then whether you laminate it face-wise or edge-wise, or you can actually make an arc shape and to improve the recovery. And then more currently, there's emphasis placed on actually unfolding a bamboo sheet and make it flat, and to make it similar to a wood veneer. On the other hand, there has been traditionally work done to produce exterior, and that can be also made into a panel product. And if you look at even the way the bamboo scrimber is produced, you can actually process the bundle and randomly place them and then press them, or you can line them up into a curtain and then press them, and more similar to in a way that the laminated product is produced. So in those different process, and pathways, then that would create a different product and different densification, because the need to create the intimate bond and the structure of the elements and how they prepared, the densification will be different. At the same time, the rate of utilization for bamboo varies as a result. So if you look at the laminated bamboo product that we normally see, that actually look beautiful and very little densification, but the recovery or the utilization is very low. And then on the other spectrum, where you can actually screen bamboo bundles and you line them up into a curtain, you put and make them, and that will actually create the highest potential for recovery.
1 minute, Changping.
So just very quickly, we're gonna just, we can also make bamboo or a strand-based product, and there's very little work done in this area. And just the final little concept that we throw up here is that we've been working with a company in China that produced a bamboo pipe for a water transportation or even underground tunnel. So it's a very innovative process where you can actually convert bamboo into strips and make curtain and wrap it into a pipe. And it has been used for many applications, including housing for demonstration. So with that, I'd like to conclude my talk. And basically, we believe that bamboo has some unique property that can complement wood for engineered bamboo product in application for sustainable construction. And however, bamboo's high density, high hardness and impermeable surface and make it more sort of a challenge for drying and bonding and hard pressing. And we believe there's a lot of potential there going forward for bamboo to learn the science and technology that has already been established for wood products. Thank you very much.
Thank you, Changping. Thank you very much. I'm glad you brought up the critical step of drying and treatment before any type of processing, and the potential for processing improvements is much needed. We've got several questions. Dr. Sastry, do you have any comments for Changping?
Yeah, very impressive. I was really, very, very happy to see so many people are doing masters and PhD. Dr. Dai, have you tried other species, like sympodial bamboos? Any work on that? And who is funding all of this exciting research at UBC? NSERC or any private companies are involved?
Yeah, you just answered the question for me. Yeah, we do. We're lucky enough to have some private company to sponsor our program, particularly Bamboo Nation, and we're able to actually match that fund through programs such as NSERC Alliance, and we also have other funding and through collaboration with our partner as well. When it comes to bamboo species, we focus a lot on mosul, but we're also looking at a species like guada, which I didn't have time to talk about, which has a great potential to be stronger bamboo species for construction application.
That's good, very good. Yeah, I'm not sure whether INBAR would be interested in joining hands with you in collaboration, because they're not they don't have facilities per se. We used to do that jointly with the universities and government labs. That's something one could explore. There are about 54, 55 countries that might be interested in developing aspects that you are outlined. Excellent work. Congratulations.
Thank you. Yeah, we have a very strong relationship with ICBR, the Center for Bamboo and Rattan, and also through them, and we also establishing stronger relationship with IMBA, and IMBA is one of the supporter for this event. We'll look very much looking forward to work with IMBA, and particularly in the education program area.
That's good.
If I can, from the question and answers, there's a couple questions about bonding, Changping. Claudio asked about the outer surface. Could it be lightly sandblasted with a very fine grain sand to allow a textured surface for the epoxy to bond? Let me give you a couple questions about bonding. There's another question that asks if with respect to the bamboo wood hybrid composites, is there any significant difference in bonding properties of different layers of the bamboo? For example, the inner, middle, outer bonded with wood surface? I'll let you answer those. Thank you.
Yeah, first of all, the sandblasting concept, and we talked about it in our group, and we, however, haven't been able to do much work, and there's been some work done by a group in Korea, and that was a long time ago. And I think it's a terrific, innovative idea worth exploring. As far as the bonding between different wood and a different surface, yes, there's a difference. Particularly, like I explained, if you laminating bamboo with wood, it's gonna for sure fade in wood, and we also explored how the inner and outer surface of bamboo can bond, and that's becoming more tricky because if you look at bamboo and to bamboo, there's an advantage and disadvantage from both sides, whether it's outer side and inner side. But for sure, yeah, you have to remove the skin.
Great, thank you. Okay, thank you very much, Changping. It was an excellent presentation. We need to move on because of time. I'd like to introduce Dr. Kent Harries from the University of Pittsburgh. His talk today is about material characterization of engineered bamboo products. Kent is a professor of structural engineering and mechanics at the University of Pittsburgh. He received his doctorate from McGill University. His research interests include the use of non-conventional materials in civil infrastructure, ranging from RFP to bamboo. Harries is a co-author of over 300 peer-reviewed articles in 3 books, is senior editor at the Journal of Construction and Building Materials, and is co-editor of the book Non-Conventional and Vernacular Construction Materials. He led the effort to revive the ISO 22156 bamboo structural design. He's a fellow of ASCE, ACI, and IIFC, and is a professional engineer in Ontario, Canada. Welcome, Kent. The floor is yours.
All right, thank you, Susan. I don't know where you got that bio from, but it sounds pretty good. Share my screen. Oops. All right, that should be working. Everybody see, can you just confirm you can see the presentation?
Looks
please?
good, full screen.
All right, fantastic. So I'm going to pick up a little bit where the last presentation left off, and we could have ordered these differently, certainly. When we talk about material characterization for engineered bamboo products, and I want to acknowledge that this is work that's been going on over many years. I've got a number of co-authors that I need to acknowledge that have certainly contributed to what I'm going to be showing today. Yusuf, many of you know Bhavna Sharma at USC, Christian Gauss, who's presently in New Zealand, and Mike Richard are all doctoral students who have contributed to this. And my colleague here at Pitt, Ian Nettleship, and Michael Ramage, who was a speaker yesterday. He'll see some of his stuff if he's in the audience today. So I want to start with the obvious. We were talking about engineered bamboo, and engineered bamboo is a composite material. And let's look around at some other composite materials, and I'll go back to my doctorate, and I work with Professor Mitchell, Dennis Mitchell at McGill, and so I like concrete. And concrete's a composite material. It's a composite of aggregate of sand, of water and cement, of course. And forgive me for the US based presentation here, but each of these have specifications associated with them. Indeed, there's even an ASTM specification for the water that's used in concrete. And these are separate from, say, the properties of concrete, compression, tension, and what have you. And so let's start thinking about engineered bamboo as a composite material also, and think about the bamboo as the feedstock, and to a lesser extent, the resins and whatnot we're using, but I'm going to be focusing on the bamboo. And so it's a little bit more complicated, I think, when we start looking at engineered bamboo, because we have feedstocks that come from all sorts of places, different species, different sizes, different growing conditions, and so forth. And these feedstocks tend to be highly variable. And so this handcuffs us a little bit, because unfortunately we all like talking about bamboo, or we all like talking about engineered bamboo, but we really need to be getting a little bit more specific than that. But we do have test methods that are out there that will quantify these materials for us, the feedstocks as it were, and potentially grade them. And that's what I want to start talking about today, is how can we integrate what we already know about, let's say, full culm bamboo, and work this into the engineered bamboo world a little bit better. So I want to step back for just a moment and talk about the suite of ISO standards that exist for building structures. They first appeared 2004, the 22156, which is a structural design document, the 22157, which is a mechanical properties document. And both of those are version 0 documents. They were sort of initial drafts. We get them out there, we stick a flag in the sand and say, this is what we want to accomplish. Took about 15, almost 20 years to get these revised into the current form that they are. And there are now 3 documents in the suite. 19624, which is the grading document, 22157, the mechanical test document, and 22156, which is the structural design document. And I want to point out a couple things here. One is the change in title. We've gone from bamboo to bamboo structures, and this is important. This is what we're talking about. And we've introduced the word culms into each of the existing standards. That's important, because this is the raw material for engineered bamboo. There are 2 standards presently under development. Hopefully both of them will appear by 2023. And these are then focusing on engineered bamboo products. One is much more focused on the product itself, so the full beam, panel, what have you. And the other focuses much more on small clear specimens. And both of those are necessary also to move engineered bamboo forward, but both of them rely heavily on the material information that we need from this bamboo feedstock. So if we look at the grading standard, I'm going to talk about briefly, because I do believe that we need to be grading the bamboo that's going into our engineered products, and I think that that can help us. And so the grading standard sets out a methodology for setting up a grading process, either visual grading, machine grading, and whatnot. It doesn't tell you how to grade, but it tells you how to set up a process. So you need to understand what's important to you as an engineer. And of course, the test standard, most of you are probably familiar with this. There are 6 mechanical tests and 4 or 5 other physical tests that are involved. So compression, tension, shear, flexure, and so forth. And so these are out there, and they've been refined significantly. So let's put this into the context of engineered bamboo, engineered bamboo materials. And so let's take a look at that strip, that piece of feedstock. And we can characterize that. And I'm simply proposing that we probably need to know things like the moisture content, the density. We could do some simple mechanical tests, compression, tension, potentially shear, the bow tie or the butterfly shear test. From these, we could grade our feedstock. We could start having different qualities, as it were. And I'll talk a little bit more about that as we go on. And what this allows us to do then is potentially direct that to our materials. Last presentation, we talked about the fact that we have relatively poor utilization for some materials, better for others. Well, if we have well-graded material, we could probably get better utilization out of it, potentially, and also split that utilization between materials. And I think this also then leads the potential to engineered layups of engineered bamboo. And so this is something that's obviously common in engineered wood. We have better quality materials if we're talking about a flexural member, at least on the outsides, away from the neutral axis, and poorer quality materials in the middle. And these could be balanced or unbalanced. So there's a lot of tests out there, and we probably want to keep it simple. We don't want to have to run 7 different tests to characterize everything. So there are some that make some sense and some that don't. So compression tests are very common. They're very well known. They're remarkably easy to conduct. They're easy to conduct in the field. They're very consistent. They generally show a relatively low variation from among the test. And one thing that's nice about them to some extent is that they're generally insensitive to the presence of a node, because the node is so small and therefore in compression doesn't have a large effect. We turn that around and look at a tension test, which is again very commonly done. We know that the results are significantly affected by that presence of the node. The results in a tension test are also affected by how we grip the coupon, the tabbing of it, the dog boning of it, and also the boundary conditions of the test frame alone. Are the grips free to move? Are they fixed, and what have you? And so tension has some problems, and so we need to be a little bit more careful when we're interpreting tension data. I'm a big fan of the bow tie shear test. A lot of people aren't. That's okay. But again, because it's a compression-based test, it's easy to conduct. It generally shows remarkably consistent results, a relatively low coefficient of variation. Once again, it's relatively insensitive to the presence of a node, and admittedly may have some limited applicability, but I have a reason for thinking about this. And that's this. Rather than having to characterize bamboo with seven different tests and what have you, trying to understand, is there a single test? And there's precedent for this. And I'm going to go back again to reinforced concrete, or to concrete, excuse me. All material parameters of concrete can be reliably established from a compression test. If I know the compressive strength of concrete, I can establish tension, I can establish modulus of rupture, I can establish modulus of elasticity with relative confidence. Can we do the same for bamboo? And I don't have an answer yet, but I'm going to throw that out as a challenge. What do we need to know? Certainly a lot of work is showing that, like wood, bamboo properties are a function of density. David Trujillo has showed density to be an important factor when we're grading. And certainly when we're dealing with full comb behavior, the butterfly shear test or the bow tie shear test does seem to give us very relevant data that we may be able to extrapolate some of these other harder to get properties from. So this is a challenge to the community. All right, so that's the first part of what I wanted to talk about. I now want to skip to after we have fabricated our laminated materials. And we did a study a couple of years ago that looked at a large number of beams. This is just a photograph of a cross section of one of them. These beams have been tested in flexure, and so that's why you see that crack in them. That's not important to what we're doing, but we're looking at quantifying actually the fiber volume ratios and the consistency of the strips themselves. And we did that using optical methods. And so we isolated each of the strip elements, we digitized it, and determined the fiber volume ratio. And this particular plot just shows 100 different strips. So in this study, we looked at 2 different materials. We'll call them M and P. The beams are very slightly different, 140 by 90 versus 120 by 60, but they all have the same 19 by 6 millimeter strip dimensions. We looked at about 60 beams all told and extracted almost 4,000 images, of which about 3,000 were usable. You get blurry image. It's not, you can't extract every image, but we have a remarkably large data set. And what was interesting immediately is that we see that between the 2 products, which are nominally similar, we have very different properties of the strips. The average fiber volume ratio is about 24% in the one case and about 19 in the other. Also a little bit more variation in this guy, a little bit messier. One of the things that's important when we're thinking about these things is what distributions do they follow? And so we also wanted to make sure that when we're looking at something and we're going to talk about random distributions and we're going to talk about how this behaves in situ, that it is in fact normally distributed, and it is. So we looked at some other things. One of the interesting little things we decided to look at was, what about the orientation of the strips from the outer to the inner portion of the cone? And so we simply tagged those and looked at those from an autocorrelation perspective. And probably for a good product, we would hope to see a random distribution of this. And a random distribution, without getting deeply into autocorrelation, would represent these values falling in that green range. So you see the green plots here are pretty much random walks between -0.2 and 0.2. That was a random distribution. In some cases, though, we saw a very cyclic distribution. So this black line on the top plot is actually representing the fact that the orientations of these strips are not randomly distributed in any way. And that's probably a function of how the fabrication went ahead, as how we went from the strips to, in this case, the vertical boards, and then laminating the vertical boards together into a beam member. And so analysis like this can help understand better the manufacturing process that we were talking about in the previous talk. And we looked the same thing in both directions, both vertically and horizontally. And horizontally, again, we saw many, many random cases, but we also saw some strongly autoregressive behavior as well, as characterized by this particular case in the black line. And again, an artifact of the lamination process, or an artifact of the process that was used to fabricate these. And this is important. I'm gonna throw up a thought experiment here for just a second. So imagine I'm just gonna take a board, it's only got 10 elements in it. And if I orient those elements in an essentially random way, or excuse me, if I take the average modulus and the average behavior of this, I'm going to come up with a moment capacity for this board, a bending capacity. And what I can do then is think about, well, how can I orient those strips to maximize the moment capacity and to minimize it? And if I do so, I can vary my capacity by about plus or minus 4%. And we showed one random case here where this particular random orientation comes up slightly higher than the average. Other ones would come up lower. Now, 4% isn't a great deal, but it does have impact on reliability analysis. And if we turn this problem around, could we be designing a process that will develop a higher quality product and take advantage of this effect? Again, it's a question. I'm not going to answer these. I'm leaving this for the audience to deal with. Another thing that we can get from this kind of analysis, so this is leading to a QC/QA type approach, were the number of nodal regions at a given cut. And throughout all of our data, again, about 60 beams, we saw that there were about 3 to 5% of these strips were actually cut at a nodal region, which makes sense. You're going to have that. Excuse me. And generally, they were distributed randomly throughout the cross section. And again, that's something we would probably expect to see. Although we could imagine that certain processes, poor fabrication processes, may not lead to random distribution. So these are things that we may need to be considering if we don't have the nodes staggered. Based on the percentage of nodes, based on a nodal length, and which I'm just arbitrarily saying the nodes are about 10 millimeters long. If I've got 3 to 5% nodes at a given cut, that's implying that my internodal length for this particular stock was somewhere in the 200 to 300 millimeter range. That will vary within your feedstock, and it might therefore have some impact on the reliability, the ultimate behavior, or the ultimate quality of your product. And then finally, of course, we know that nodes are a little bit of a problem in tension because they have a lower capacity. Is there a way that when we do have issues with nodes, can we move the nodes, let's say, into the compression zone where they don't have as much effect? Is there a possibility to take advantage of these kind of behaviors and again, improve and come up with engineered layups, but potentially by grading? Grading may be based on internodal length, as an example. And one last concern, and I know this is going to come up in the panel discussion, so I won't spend a lot of time on it, but we've talked about bonding and glue line. And so in general, if I have a strip of bamboo, very, very roughly, the fiber rich side is going to be more hydrophobic. The fiber poor side, the inside of the column, is going to be more hydrophilic. There are studies that look at the bond capacity of this. I know we talked about this in the last session as well. This was a very nice study that was put together a few years ago, where they simply bonded these strips, bamboo to bamboo, outer to outer, reversing it inner to inner. And you can see that the bond capacity differs by about 50%. They didn't specifically test the outer to inner, but one would assume it would have a capacity similar to the inner to inner, because obviously the weakest link will control. And so this is an issue that we do need to address. It's an issue that is largely unique to bamboo because of the functionally graded behavior. It may impact, as we discussed only a few minutes ago, it may impact adhesive selection. It may require a degree of standardization. And how this range of hydrophobicity, that's a very hard word to say, but how that range affects things like scrimber could also, may also be an issue. Now, when I look at these numbers and I see a poor behavior of 2, or a lower behavior, excuse me, of 2 MPa, I'm still not overly concerned. When I think about the mechanics of what we're making, that's probably going to be a pretty darn good product, even at 2 MPa, but not in every case. So I'm going to conclude. Hopefully I've not taken up too much of your time. We have a little bit of time for questions. I'm making a bit of an argument, a bit of a plea maybe, to look at the feedstock. Let's not talk about bamboo. Let's talk about grades of different species potentially going into the feedstock of our engineered bamboo. We can do this. We've got the existing test methods. We've got the grading protocols. This could lead to engineered layups of engineered bamboo, and similar to what we do with engineered wood. And I would argue that this is actually a much simpler process for engineered bamboo than it is for the full comb applications that I tend to focus on. From a manufacturing perspective, and this is important, I think, that we may want to start looking at the effects of random distributions of these material flaws. And the flaws are primarily the nodes. And of course, in bamboo, we can't avoid those nodes. They're going to be there. And again, this might lead to grading. It might lead to enhanced reliability. And it might even lead to different machine design in order to affect a more efficient fabrication process. And then finally, a question that I think has already been asked, so I will ask it again. We need to understand how the inherently graded nature of bamboo affects the glue line behavior, affects that composite behavior. And so with that, I will conclude, hopefully on time. Hopefully everybody could follow that, and I wasn't speaking more quickly than I usually do. And I invite you all to NOCMAT. I got to get that in next month. So with that, I think we're into questions, right?
Oh, thank you. Thank you very much. Yeah, you talk fast, but you really know your subject and deliver it very well, Dr. Harry. So thank you very much. It was excellent.
Did everybody get my hand movements? That's the important thing, because it's that French Canadian thing. I gotta talk with my hands.
I think they might have been fixated on your slides, but yes, your hands are good too. Dr. Sastry, I'll leave it to you.
Yeah, I agree. You made us all exciting. This so complex a subject to make it look as so it's very simple. One question, Dr. Harris. I saw in one of the photographs you're using sympodial bamboo, the small diameter ones. Is that true for your testing?
No, I don't know what photograph. Everything I've used here, obviously working in the Eastern United States, I import everything. I'm usually using Moso. I also have access to Guadua and a couple of other larger species.
Okay.
We do nothing small here.
As you know, the excellent conclusions, but it depends on the species. There are species variation, especially if you're talking about millions of hectares of sympodial bamboos. Your research could be a great savior to some of those countries to produce these composite products.
Well, let me actually answer that because this is an important issue. Obviously, species is a huge issue along with condition of harvest, the whole thing. And so what we're trying to do, we're not focusing on the data. I don't really care what results I get. We're focusing on the mechanics and what it means. And we believe that we can treat bamboo with a material informatics approach, is that if we generate enough data, start understanding what the microstructure, what the macrostructure is doing, we can use data techniques to help to feed and help to better understand what we're looking at from a feedstock. Now, we still have to do testing, there's no question, but it can help direct it a little bit better. It can help direct us away from species that may have a problem that we don't immediately see. It may direct us towards species that work a little bit better for certain processes. And so a lot of our work, and particularly Dr. Nettleship's work here, is focusing on pushing bamboo into the material informatics world so that we can actually learn from it and so that we're not overwhelmed by the need to look at 100 different structural species coming from 1,000 different sites around the world.
Very good. Thank you.
Okay, from the Q&A, how about this question? How representative these tests of comb sections are for the whole comb, taking into account the fiber content difference along the height of the bamboo comb?
Well, I mean, I think when we're talking about engineered bamboo, that is something that is supposed to, should be also randomized. And so we do need to, again, we had of images that we were able to process with confidence, we had over 3,000 strips from commercially available material. One has to assume that within that sample, we've got stuff that's from very low in the comb, we've got stuff certainly middle of the comb, and whether the top of the comb was used for these materials because they're higher quality material or not, I'm not entirely certain. Again, these were beams that were tested previously, actually by Bob Sharma and Michael Ramage at Cambridge a number of years ago, and then we took cross sections of the beams to really just look at essentially a QA/QC on the beams themselves.
Okay, and one further question before we move to the next speaker, and I'll remind the audience that we will have a panel discussion and we'll try to address more of these questions. Thank you. But one last question for Dr. Harries. Can acoustic tools be suitable for the NDT testing and grading of combs before conversion?
I know a lot of people are looking at acoustic methods. I have not tried it with bamboo. I have done a lot with guided wave work on other civil infrastructure. I have some significant concerns with its accurate use in bamboo. However, if you have a fairly consistent source and some good training data, I suspect it is a good approach. But it's going to be a function of so many things, and it's everything from moisture content to density, internodal lengths, all sorts of things that are going to come into play. I think it has a lot of value, but when you have a good controlled source, a good controlled source of bamboo.
Excellent. Okay. Thank you for that. And thank you very much for your excellent presentation, Dr. Harries. We'll move on now to Neil Thomas. Neil's our next speaker. His title is Bamboo, This is the Future. And I'll quickly read a little bio on Neil. He's founder and director of Atelier One, which has been described as the most innovative engineering practice in the UK. 2014, he was elected Royal Designer for Industry, honorary RIBA fellowship for both excellence and the inventiveness of his contribution to architecture over the past 25 years. And in 2015 was awarded Fellow of the Institute of Structural Engineers. He was honored with a MBE on the Queen's 90th birthday for contributions to architecture, design, and engineering. And he received the Milne Medal in 2019. Since visiting Bali over 8 years ago, Neil has become more involved with the design and development of bamboo structures. He's a regular lecturer at Bamboo U, an adjunct of the Green School Bali, teaching the engineering principles behind bamboo design. He also holds a number of high-profile posts in the UK and US educational service, most recently being a visiting professor to Yale and MIT, and he recently wrote the technical appendix for Bamboo Contemporary, published by Princeton Press. Let us welcome Neil Thomas. Thank you.
Thank you very much, Suzanne. Thank you, Chung Ping and Dr. Sastry. I have to say, hearing the two previous speakers, it's kind of unbelievable in the 10 years that I have been involved with bamboo, how much it's changed and developed and how quickly things are moving now. So what I'm going to show you, I'm going to turn my video off because sometimes the signal's a little bit, the bandwidth's a bit poor. I got into, I run Atelier One Structural Engineers with my partner, Aaron Chadwick, and we've been involved in an interest in materials and specifically how to take advantage of the properties of materials. And we've been doing this a long time with timber, which we call the known material, the known natural material. This is a tall timber tower that we actually developed with Richard Rogers Architects and Michael Ramage from Cambridge. And the thing that you start to look at tall structures with timber, and the thing that becomes very apparent is because of the elasticity of it, the low modulus, you need to think about structures in different ways. So here what we did, you can see, is pull all of the structure out to the extremes of the building, such that we increase the lever arm, reducing the forces and understanding the fact that it's a fairly elastic material. It's a very important thing to understand how these properties affect the way you look at design. This is a building for Woodland Trust, which is a building in the north of England, which we developed with Field and Clegg Architects. It's a 3-story building on the right, dropping down to 2 and 1 on the left-hand side in that sort of spiral shape. But what's interesting about it, made from CLT, we did something that we eventually won an innovation award for. If you look at this image here, down the center of it, the CLT spans left to right across the beam down the middle. And those white panels you see are concrete panels, and they are used in the summertime. So the air is passed across it. But they do 2 jobs. They act structurally, and they are composite with the CLT. And we did a hell of a lot of research because it's the interface and that joining of the composite sections together that is the kind of very difficult thing to consider because of the different, again, elastic properties of the materials. The building, actually, interestingly, when we first talked about the idea of doing it in timber, the quantity surveyor, his argument was that he was pricing it 25% more expensive than concrete. And as it turned out, only when we went through the process of design, they became comparable in cost. So there is this kind of misunderstanding that timber buildings, particularly at the moment, are more expensive. I think if you design carefully, that is not true. I wanted to show the kind of how far we've gone with the kind of idea of CLT. This is the British Pavilion at the Dubai Expo, which has gone through this last summer. This is a design done by Es Devlin, and it was a whole series of CLT cassettes. That was the computer image. This is the finished building. And it's quite unbelievable, built in Germany, and the kind of level of CNC and machining that you can do now. You can achieve 3-dimensional forms with CLT, and it's quite remarkable, quite amazing. But there is something about engineered timber. Those are all timber buildings. There's a kind of a level of wastage. And I think if we are considering sustainability, not purely just in the terms of the engineering of it, but the usage of the material, how you use it. And I just wanted to show you this. This is a little project at Hook Park in the south of England. And they said, it's the AA, from the Architectural Association of England, and they were looking at building a storage facility. And they have 120 acres of forest there. And they said, well, hang on a second, instead of cutting the timber up into straight sections, losing its strength actually, or reducing its strength due to the circumferential the breaking down of the circumferential rings, they said, what if we take a piece of structure, design the idea of it, and then go and scan around the forests and see if we can find the pieces to match what we're trying to do. And then you take 21st century technology, CNC machining and robotic machining, and you start, what they did was, that's the Y piece that you saw in the image before. there being machined to form a series of nodal connectors between it and the adjacent members. Those connections are formed as male-females, and because the form of the arch that was built in the end is in pure compression, it never goes into reversal, there are no actual physical mechanical connections between those elements. And so you see there, they built a truss which is held down by the self-weight of the roof. And although there are kind of small elements you can see crossing over, which provide additional shear resistance, the bulk of it's built from the elements of the tree as it came, using 90% of the kind of the element of the tree itself. It's interesting because this is a kind of relatively, for us anyway, relatively recent development, and it kind of talks about the way we've been thinking about bamboo. So I mentioned I was introduced to bamboo 10 years ago by this man, John Hardy, who is the owner and starter of the Green School in Bali. And the Green School, if you know it, is entirely made from bamboo. The whole school, and the school, it's built from straight sections of Dendrochlomis asper, is the majority of the bamboo they use. But the Green School itself, all of the buildings have no walls to them. So it actually not only physically doesn't have walls, but it kind of metaphorically doesn't have walls either. It is one of the most amazing places I've ever been to. And it introduced me to the possibilities of bamboo, which I hadn't even realized the fact that you could use it structurally prior to that. They showed me this building, which was designed and built by Jorg Stam for John, which is called Three Mountains. And it uses, Jorg is a big fan of Friato. And you can see here, the tower's built as kind of compression forms using three-dimensional shape stiffness to give the stiffness. And then the roof elements, you can see, they are using bamboo in tension, in pure tension. They were building houses. Elora Hardy, John's daughter, she's developed a practice called Ibuku, or mother, and they've been developing houses and building houses throughout the whole of Bali and Indonesia for about the last 12 years. We got involved with them, and then we began to look at the properties of bamboo, and it took a very long time before we were willing and able to say, actually, we can design with bamboo, because of the nature of bamboo, to understand it, it took us a couple of years before we were able to do it. And we started small. So this is a kind of small canopy. It's a house, actually, an open house that we built called the Moon House, engineered. But it uses bamboo in elastic bending. So we're beginning to discover the possibilities using the properties of bamboo. So it's bendability, elasticity, and the fact that we can create shape stiffness, create the shell form out of small diameter bamboos. John's son, Orin Hardy, he runs a thing called Bamboo U in Bali, which if any of you ever get the opportunity to do, I would recommend you do. And they do an 11-day immersive course. And they're the students with all the local specialists, bamboo carpenters, and they build a series of elements which is building on the kind of facilities for the school itself. So this is a series of basic high paths. This again we developed with Jorg, but it's using straight sections, using again shape stiffness to help us form the kind of roof. And we've gone a lot further now. So from working on these smaller projects of natural bamboo, this is a project for a new green school in Tulum. And this is the heart of school building, which we developed with Ibuku, with a much greater now understanding of bamboo. And here we're looking at small diameter bamboos and creating, again, much larger three-dimensional forms. But the kind of one of the major issues when you're working with bamboo in its natural form is how you make the connections. And connections are critical. And this is where, as I said, understanding the properties of it are fundamental. The bamboo we're working with is very good in compression and tension and very poor in shear. And the reason for that poorness in shear, as Kent showed, Chungping showed, I think in an early slide, all the fibers are longitudinal. The vascular bundles run up and down, and there's very little strength circumferentially. And that means you have to think hard about it. So these details, these pin connectors, they are working in shear. And so the kind of design and the possibility of some of these buildings are limited by this ability to be able to connect them. And we saw a bamboo bicycle and said, hang on a second, there's something going on here, because what it's doing, what that sleeve does, is stop the bamboo bursting open. So splitting in its longitudinal direction because of the weakness. So we started to look at taking that idea of a sleeve around the bamboo, added the internal prongs, so that now creating a connector for the bamboo, which would provide resistance to buckling inwards and resistance to buckling outwards. Then you have to think about the fact that bamboo is not uniform. So we developed a series of stepped connectors. And the gray shows the element that would be either some kind of injection molding eventually, but initially we 3D printed the sections to look at how they worked. And this is what we eventually came up with. So you can see the difference in the bamboo, and the connector has a step in it, and it has these canals, and you put in this putty. My children, 3 daughters, all do hockey, and they use this thing that you put in a mouth guard, where you have the main guard and then you put this putty in and it fits. So what that does is it means now we've got a complete full connection to the bamboo. And oddly, interestingly, the bamboo now, that piece of bamboo, those 2 pieces now think they are continuous, which means we could start to do things like this. This is actually a roof we engineered in Melbourne. It's in steel, but the principle of it can be done in bamboo if you can make bamboo continuous. The same, the Mannheim Bridge Shell by Proyotto, which is one of the most beautiful buildings in the world and being refurbished right now. It's possible to create that, the type of structure, and very much kind of one of the ideas we were looking at for Tulum, or we were talking about as an idea for Tulum. And also looking at a structure for John Hardy for a congregation space, which is called the Great Hall, which combines not only the idea of 3-dimensional form, the idea of the connection systems we talked about, but also environmental devices like the towers, the black bodies on the face. And as the sun heats the black body, you get air drawn across the surface beneath, so you get free cooling from using these towers. Which brings me to engineered bamboo. So, as I said, over that 10-year period, we've done a hell of a lot of work looking at it in its natural form. But the last couple of years, it's become more and more, and the work again that Kent and Chumping showed earlier on, it's unbelievable, really, the level of information that is becoming available. But what's amazing about it is if you look at this diagram and the figures you see for ordinary timber, you know, if we're looking just purely in compression, GL24 timber at 20, Bowerbook, which is the densified timber we looked at using on the tower that I showed you in the beginning. And then the Renewtech Verilam, which is a product produced by Luke Stewart in the United States, he's talking about member properties that are way higher. And I mean, look at the tension he's talking about here. These properties have been verified by tests, according to him. Interestingly, they are currently starting to build in the United States. Moso have recently got a technical approval, first European technical approval for their bamboo to be used structurally. Everything's changing. That's the product that Renewtech produced, which is radially laminated bamboo, or radlam they call it. And because what it does, it doesn't remove the outer skin where the very dense vascular bundles are the strongest part. That's how he's managing to achieve some of the properties it is. And I said it's about, as an engineer, my interest is in the things I'm talking about saving materials, how to think about the way structures work and using these properties. And we often draw on nature, and this is the idea of the palm frond, which is you use plates, folded plates, to give it stiffness, which is how these leaves can be so large. And we were invited by British Land, a developer, to see if we could replace a concrete and steel structure within a standard building they were doing of a 9-meter span with natural materials, either timber or bamboo. And this is what we came up with, the idea of a folded plate. So That's their structural floor on the left. And with a 5-inch concrete slab, 6-inch concrete slab, and then the steels. And on the right-hand side, the depth of the zone in between is they use the floor as a plenum for air movement. So we did exactly the same thing, but in a series of troughs on the right. And there's another unbelievable thing that happened about this. If you take a piece of timber flat and you burn it, so you go through the tests for fire, it reduces in strength in a 2-hour fire, we looked at in this, by up to 60%. Because of its inertia, its form, its shape here, its stiffness, you reduce the strength of it by only 40%, meaning you can use less material. The depth of it also meant that we could deal with vibration, and which is very often a major influence in the design of timber structures. So that project was, the development of that project was done just before COVID happened. And at the moment, there is not really an appetite to look at building or working on new office buildings. We are looking at some other projects with various other people. And one of those I'm going to talk about, which we actually work on with Chung Ping. But there's another thing that we looked at during the development of the flooring system is, what about looking at the optimization of connections? Because you have certain conditions that you need, forces you need to transfer. And because the material's different in compression, different in tension, very different in shear for bamboo, what about you look at forming connections between them in a way that takes advantage of all those properties? So we began to look at this kind of idea of Japanese joinery and how you could machine the connectors so that you get better and more optimized force transfer. And the thing that we're looking at with Bamboo Nations is, again, we looked at the idea, well, it came about through the process of the design we were looking at, that nature, again, won over in the argument. So it's a project to cover 2 basketball courts. And what we were trying to do is look at it using engineered bamboo, how to use it, how to develop the project so that it's using it efficiently. And we looked at a whole series of different frame types. This is in Niagara Falls. And so we had to consider the fact that it's kind of a very, very heavy snow. So the barrel forms, standard portal frame forms, pitch roof. But the one that won out is the dome arrangements, A and B. Here you look at the deflections. So this is the barrel. So 120, the asymmetric load was 400 kilograms per square meter, which is, I don't know it in pounds per square foot. I'm sure you can work it out. 400 kilograms per square meter of asymmetric load, nearly half a ton per square meter. 129 millimeter deflection, the same deflection below 92 millimeters. On this frame, 91, and the domes, 42. So by thinking about the form of it and kind of looking to nature and shell forms, we were able to reduce the structure down. So the barrel arch had 133 meters cubed of bamboo, the portal frame 144 meters, and the bamboo dome 104. So less than 25% reduction. And this is purely the first level of exercise we've been to. This is kind of the basic analysis, having looked at the various forms. I am sure through careful design that we will be able to increase that difference. And the point being, the less material we're using, again, this is what we should be trying to do in the construction industry and in the engineering industry, which I'm in.
Excuse me, Neil, you have 5 minutes.
Thank you. And I want to end on a project which is a kind of culmination of the 10 years of I've been backwards and forwards to Bali. I teach at the Bamboo U I mentioned, and I travel backwards and forwards there. We're looking at projects with them all over the world now, but this is one we completed for the Green School recently. And it was developed with Ibuku and Elora Hardy, the architects, with Jorg Stamm, who is known as the bamboo prophet, and I think considered to be the best builder of bamboo that I know. And he came up with the idea, the basic model idea for this form for the new gym, a series of crossed arches and then shells between them. So, and because there isn't any information on this stuff, so we were building composite sections, putting together the natural bamboo columns. So the only way we could kind of understand how they were working was to test them. And as then that's what they did. You can see there. So we did a huge amount of testing to understand the arch forms and also the shell forms. And the shell you're looking at here, this is one single section from the roof. And it uses bamboo splits to form the three-dimensional surface, and then shingles attached across the three-dimensional surface to give it shear stiffness. So the test's crude, but they gave us all the information we needed to be able to continue to develop the design. And you can see the bamboo arches are formed from 14 centimeter asper columns in a group of 6 combined together, or partially composite. And then the whole thing covered in bamboo shingles to provide the water. There's a waterproofing membrane beneath it, but the shingles on the outer surface. And the thing about it is, it's the form inside. Elora is amazing as an architect. She kind of knows and lived with bamboo since she was a baby. And she kind of knows and understands how it works. And this is the kind of form we developed. So we've been pushing the kind of nature's three-dimensional form, but more also the understanding of how to make composite various other elements within the kind of world of bamboo. And you see here the anti-plastic surfaces provide this stiffness so that the whole building acts as a single thing, as a single structural piece. And that is really, I wanted to just show how we are applying some of this tremendous work that we've already seen earlier today into some of the projects we are currently doing. And as I said, it's mushrooming, it's massive now. It's becoming more and more all the time. We are being asked to look at and consider the way how bamboo can be used to complement timber in the construction industry and help make a more sustainable future. Thank you very much indeed.
Thank you, Neil.
Hello.
Hello. Very inspiring. Excellent. Thank you. I'll allow Dr. Sastry to comment.
I second that. You know, I was very impressed with the variety of all those marvels you've shown us. Beautiful and sports arenas. Now we need to, as you say, bamboo, the future. We need to concentrate on bread and butter things, ordinary housing. Some years ago in Bangladesh, we developed a kacha house using bamboo for $1,000. That was a great achievement. That was 30, 40 years ago. Now, these beautiful structures, especially the one in Dubai showed us, my God, that was unimaginable some years ago using. That was fantastic. So how is this green school in Indonesia? That's a country with a lot of bamboo and all that. As I see it, there's too much of material requirement to build these structures and all that. How practical are these, for day-to-day living, for houses? Good to show them, attractive, but we need to concentrate on, day-to-day use houses, like.
No, Dr. Sastry, absolutely understood, completely understood. And I think there's a huge amount of work being done by people, and we're working with various people, Luis Felipe Lopez in the Philippines, and we're looking at a housing system in Mexico at the moment. Yeah. But and the thing about it is, I kind of showed all the stuff that was rather beautiful around the world, just to kind of show or try to express how through doing these things we're understanding bamboo, we personally as engineers, and that we can share that information to this group of people, under the larger group, about our understanding of bamboo and then what they can do with it.
That's good. Yeah, why I'm saying that is, I have a friend who have was planning on setting up a bamboo kind of village in Niagara Falls area. And of course, he talked to some of the experts, including Susan and Dr. Dye and the ones in Hawaii, So that's, from that perspective, these are beautiful possibilities. Let's come down to the ordinary level. And if this man is interested in setting up something in Canada, he comes to you, we need to be prepared to come up with practical, the design so that it's cost-effective design. I like that, the sports arena, beautiful. That and then the bicycles and many other things. Yeah. No, that's
Thank you, Dr. Sastry. Thank you.
Thank you.
Okay, we let's take one question, and then we'll have to move on to the next speaker until the panel discussion where we'll deal with some of the other questions. Thank you very much. But there's a question here that says, Neil, are you familiar with the use of crock frames in England? These are centuries old and could easily be adapted to bamboo. You have a comment on that?
Crock?
Crock, C-R-U-C-K, crock frames.
Yeah, I am familiar. And I think another presentation would be to go through. I mean, the thing we were looking at there with Chongping and Seoul, where we were looking at different framing systems to kind of make more efficient bamboo. I mean, we've been through a number, but certainly I am familiar with it. I know what it is. I mean, the ones we chose for that particular thing. But as Dr. Sastry said, I think the housing systems we're looking at, the kind of issues are often earthquake, and so we have to consider very much the question of earthquake in the particularly for disaster areas and the housing systems, which is what kind of tends to drive it. We are trying to avoid using heavy materials, hence the connect.
Yes, Neil, we're having a little problem with your audio. Neil, perhaps you should shut off your video for your bandwidth. Oh. Well, I'm hoping you can hear me, Neil, but I do think your comments about connections, whether we're talking about the whole calm or the engineered bamboo, is excellent, and the exploration into connections is ongoing. And thank you very much for your comments and your great presentation. I appreciate you joining us today. We need to move on now to the next speaker, Dongshen. Oh, you're welcome. Thank you. Dongshen Huang from the Nanjing Forestry University is our next speaker. His title is Engineered Bamboo Composite as a Construction Material, Opportunities and Challenges. Dongshen, you have the floor. I'll read you while the tech is getting your presentation up. Professor Guang is a PhD in engineering. Graduated from the Southeast University in China, specialized in civil engineering. Before 2004, he took a position as structural engineer at China Real Estate, Hefei Limited. He was awarded the National Top-Level Structural Engineer in 1998. After 2004, he joined Nanjing University of Aeronautics and Astronautics as a professor in the Department of Civil Engineering. And in 2008, he took a position of professor at the School of Civil Engineering, Nanjing Forestry University. He's currently the director of the National Engineering Research Center of Biomaterials, NFU, and the president of Southport Innovations, an institution of biomaterial and structural research. I'll hand it over to you, Professor Guang. Dave, can we have some technical assistance, please?
Yeah, it's on his end. His camera's just showing us black. His microphone is open, but we're not hearing anything at the moment.
Suzanne, can we move on to the next one while he's sorting it?
All right, thank you very much. Okay, our next speaker is Alireza Javadian from KIT Germany. His talk is the engineered bamboo as reinforcement for structural concrete. Hopefully he's ready to go. He has a PhD in architecture and construction from ETH Zurich, and his master's degree specialized in construction materials as well as structural engineering from NTU and NUS in Singapore. Oh, now we have Professor Dongshen's. Okay, hold on a moment.
Do we have audio? Dongsheng, does your mic work?
Okay.
I think maybe we'll have to, I'll just take that down and allow.
We'll rearrange the program.
Yeah.
Dongshen, if you can hear us, I hope you can hear us. We're going to switch speakers. We'll have you go next after Alireza Javadian. Dr. Javadian, are you prepared to start now?
Yes, I can. If
thank
I
you.
can share my screen.
Yes, thank you.
Okay, perfect.
Back to the regular schedule.
Thanks, Dave.
Okay.
Okay, perfect. Thank you, everyone. I think I should say thank you to also to UBC, to IMBAR, especially Professor Dai for organizing the event. I think there was a very long time that we didn't have an event on the use of engineered bamboo, a topic that in the last 10 years being really researched a lot across the world from Europe, Asia, and now I can see a lot of research also being carried out in the US. So this is a part of research that we have been doing and continuing from the time that we have been at ETH in Zurich and then in Singapore and now at KIT in Germany. And it was all the research basically started for us, we were not familiar with bamboo. I didn't have any experience with bamboo, nor the team. We were all mostly architects and structural engineers, but we started to look into the problems that the world is facing the next 50 years, 60 years, 100 years. And that's the problem with urbanization, where we need a lot of materials and for building, for construction, and for many other projects that the world is basically needs. And that prompted us to look into the major countries, the major users of or major consumers of the materials, especially building materials. And those countries are the countries that are mostly are part of the developing and mostly also part of the developed world. But what prompted us also was the three major challenges that the built environment at the moment is facing: the amount of CO2 that we are generating, and the demand for housing in the next 80 years. And finally, knowing the fact that majority of the construction material that we are using are non-renewable. We have really finite resources. I think all of us, we know that cement, we use concrete, all the ingredients, all the minerals are not really renewable in the time frame that we live on this planet. Therefore, we started to look into the fact that not just steel reinforced concrete is one of the major material that being used today as of the in any world, especially in Asia, Southeast Asia, either developed countries or developing countries. So we started to look into, is there any alternative? And that's what our research started when we were based in Southeast Asia. We started to look into the locally available materials. Of course, when you go to Southeast Asia, you can see that a lot of people traditionally been using bamboo, especially natural bamboo in its raw form, as what some other speakers today and yesterday they talked about. It is a very, very common material which is available almost, that's what they call the bamboo builds from Southeast Asia, Central America, Latin America, and even in Africa. We have really good bamboo resources. And for centuries, they have been using bamboo because it's a fast-growing species compared to timber. Bamboo grows less than 5 years, and it has really amazing mechanical properties that was highlighted today by Professor Dai and also other speakers. And that, of course, it was very interesting for us as engineers, especially as structural engineers, and also for our team members as architects. But also the other fact about bamboo is that it helps a lot with deforestation. This is a map of Southeast Asia, especially covering the Indonesian part, Borneo Island, and those regions that it can show that in the last 50 years, almost majority of the forest, the natural tropical forests are gone. And no, unfortunately, they have not been replaced, and nor the government has any intention to do so, because mostly they are replaced by either pulp plantations or for agricultural lands. And that shows that deforestation is also remains a challenge. And that's where bamboo as a natural material, as a natural plant, as a fast growing plant, especially could play a very important role in that sense. So if we talk about the whole life cycle or low value change of the bamboo industry, we can see the benefit comes from every angle. So we have started to basically do a lot of research. We have started to look into how people in Asia especially are using bamboo traditionally, but we have started to realize that using bamboo in its natural form as was described is very interesting, is amazing. But the problem is that if we want to be an alternative, sustainable alternative to timber, to steel, to concrete, we need to be a little bit, sorry to say this, to need to be a little bit sexy. And that means that we have to transform bamboo into an industrially viable alternative. If you say, for example, in Singapore, we had a very hard time to convince the agencies for funding, because when we talk about bamboo, for them, bamboo is poor man's timber. So we started to see how timber in the last 40 years, 50 years, being regarded as a material of choice for many countries, especially in Europe, for example, in Australia, in North America, especially engineered timber products like CLT, LVL, glulam. So we thought that we should develop, or we should learn from those technologies and adopt it to bamboo fibers. Of course, it was challenging. It took us 4 or 5 years to develop methodologies in between the current methodologies that being used by several of our panelists here and also other researchers. But what we did was the formula of the treatment of the fibers, and of course the type of adhesive binders that we developed together with our industrial partner from Germany. And that helped us to really move on to making the bamboo into an engineered product which is more industrially acceptable. But before that, we focused on one of the most common species of bamboo globally and also in Indonesia and Southeast Asia, which was Dendrocalamus asper. We really did a very, very deep analysis of the Dendrocalamus asper. It was a couple of PhD and master students who worked on this project. So it was not just me. So it was really, really a big team work. And they managed to collect Dendrocalamus asper from all over Southeast Asia, from Indonesia, Cambodia, Thailand, and even Vietnam, and all the way to Philippines, to really see what are the range of the properties that Dendrocalamus asper has. And then we classified it according to the wall thickness, according to the tensile strengths, according to the flexural strengths. And the students, together with the team, we developed some statistical modeling to be able to predict some of these properties, because it's not really possible to test every single bamboo column, especially if you talk industrially, how it's being done in timber industry. You can't really test every single bamboo column. So you need to know, for example, if you ask for a supplier to give you 100 columns, what are the properties? If you test one, maybe it's interesting, but what are the other? How about the other 99? So this modeling helps us a lot to estimate the properties. We also did a verification to compare the formulation, the models that we develop compared to the real value. So we did almost 1,000 series of tests with the models and 1,000 series of samples with the real actual basically testing at ETH in Zurich and also at NUS in Singapore, to see how the model validation works. And the model was quite, to be honest, quite accurate. So it was very interesting. But of course, this model can be only applied to Dendrocalamus asper that can be collected within Southeast Asia. So as I said, 2 things very important, or were basically developed through this research. What was how we can process the bamboo into fibers, certain thickness, and of course that detail can be easily found in our paper. So I don't go really too much into detail, but also the state-of-the-art formulation of the binders helped us a lot to achieve really high strengths that I will show you later. So
Hi, sorry to interrupt. Your microphone's distorting a little bit because I think you're holding it a little bit too close, so your breath is causing it too. So if you could just hold it a little bit further away and a little bit off.
Sure. Thanks for reminding me. Thank you. So what we developed, we call it bamboo veneer lumber. So as was highlighted today, is a composite material. Instead of timber fibers or wood fibers, we use bamboo fibers and a binding technology into what we call it an engine. So it's a type of engineered bamboo product, but it's a name that we chose to be able to differentiate it from the other engineered product in the market. So we did a lot of mechanical testing like tensile tests, and the average for this specific species of the Dendrocalamus asper in Southeast Asia, we achieved the tensile strength in the range of 270 and the young modulus of 30 gigapascal. Similarly, we have done a lot of flexural tests or bending tests, and the bending test and the tensile test, they were quite close. And finally, compression test we received along the fiber direction. Of course, the mechanical properties were quite interesting. So this is also a range. So what we did at the end, we also decided to focus on production of Dendrocalamus asper from different part of the Asia. So we did, of course, in earlier time, focus on the Indonesian part, but we said, okay, that's not possible. Just focus on Indonesia. Let's produce a BVL with different Dendrocalamus asper from Southeast Asia, and that's what the range that we achieve, and that shows that even at the lower quality Dendrocalamus asper, in terms of bending strength or flexural strength or MOR, the mechanical properties of the engineered bamboo products that was developed is still much higher than the glulam, basically glue laminated timber. And shows that there's a huge opportunity for engineered bamboo products like this to be really employed by the construction industry. So we had a lot of applications, but one of the very interesting bond that we did was very, I would say, very first time, because we have seen that in the past there were really strong focus and a strong research on using natural raw bamboo as a replacement for steel. In Brazil, Professor Rabwami did a lot of works on that. Also, we have a lot of works that have been done in Germany in the past and also in China. But the problem, of course, with natural bamboo, as we all know, is the shrinkage, is the thermal expansion, and also is the problem with humidity, water. So, and then you have debonding and then swelling. So we decided to transform our BVL into a replacement for steel. So we had to prepare a specific mold to be able to transform or to bend and prepare the stirrups or the shear reinforcement. And of course, this was a very challenging part because especially at the corners, we didn't want to lose. So we had to adjust the thickness of this stirrup to ensure that we have sufficient shear capacity, tensile capacity, and bending capacity at the corners. And then one of the other important, I think, Professor Dong, yeah, hear something. So I think one of the important factor was to ensure that how this new reinforcement system, the unused material, can bond into the concrete, because bonding between concrete and steel is perfect because they have similar thermal expansion coefficients, but between bamboo composite, which is a fiber reinforced polymer in general, somehow is not as easy as the one with concrete. So for that purpose, we needed to apply a special type of coatings, again developed by our company, our collaborator or our partner from Germany, was a special type of coating that would allow a certain thermal expansion coefficient or transfer of heat, so to ensure that the debonding does not occur. So the result also, we monitored all the results through pull-out tests to ensure how this bonding and this coating works well. So we had to, of course, work with the company to ensure that we can modify the coatings to ensure that the bonding can be maintained during different type of loadings. Because the moment you lose the bonding, there is no point of having reinforcement replacement with BVL, because the moment you don't have any binding, so there's no transfer of forces, and that's basically means no reinforcement in concrete. So we also, of course, we developed some models to predict all those bondings, especially in terms of thermal stresses. That was a very important factor because thermal expansion coefficient of bamboo composite or engineered bamboo are very different from steel and concrete, and that could definitely cause an issue when we're going to use it in environment that we have a really huge huge difference between the thermal capacity of the outside and inside of the concrete samples. So of course, at the end, we put all this into the concrete. We did a lot of tests, and we monitor the cracking behavior. I don't go too much detail on that, but I want to highlight on this one, which we designed all these beams together with our students based on the American Concrete Institute's fiber reinforced FRP design, because we see that's the closest type of material to what we use as an engineered bamboo, because we have a composite material, we have a polymer in it. So we decided to follow the ACI FRP design, FRP reinforcement design, and the results were quite, I would say, to us were surprising, because as you can see here, as you can see here, the green one shows the failure loads that we achieved through the test, and of course the failure loads that was achieved through the design values were the red ones and the nominal failure. So in general, we see that in terms of capacity, the FRP, the engineered bamboo has a capacity to be used as a steel reinforcement. But of course, there were challenges, because when we started to design, so basically we brought all these design values, but we designed some houses in basically with the CAD models. We realized that when we go above 2-story houses, when we bring in the factors from earthquakes in earthquake regions, when the factors go higher and higher, so when we're gonna have area 3 or area 4, area 5, especially for based on the Asian codes, we're gonna have problems, especially with the elastic modulus, because elastic modulus of engineered bamboo or the BVL we had, of course, relatively high compared to timber, 25 to 30,000 MPa, but still is not sufficient to reduce the deflection. And then when the deflection limit comes in, then you need basically larger sections, and when you start to have larger sections, then you will have problems with architectural design. So it won't be as I said before, maybe as sexy as a steel reinforced concrete. So that was the challenge, and that's the research that we are still continuing to see how we can improve the elastic modulus, or how we can introduce design philosophies that even with lower elastic modulus, we can achieve similar design values as a steel reinforced concrete. So for now, what's based on our work, our recommendation was to use it in a lower squeak zone and less than 3-story homes, and that's something that we have been working on that, and we hope to be able to extend our research to other bamboo species using our technology to be able to also evaluate the properties, especially the bamboo species from Latin America, Guado. We are very interested. We have started to do some basic research on that, and hope that in the next 2 years we can have some valuable results to be able to share. And of course, again, what we do is part of our work to be able to follow sustainable, or to contribute to sustainable development goals. And we see, at least through our research and many of your research that you do amazing works around the world, we can at least contribute to 6 of the sustainable development goals with using engineered bamboo, and also promoting the use of or growth and plantation of bamboo all over the world, that bamboo can grow. Yeah, I think this is my last slide. I would be happy to connect it to whoever like to be able to like to know more and would like to collaborate with us or to contribute to our research. Here is my contact information. We'd be happy to connect to you if you like. Thank you very much.
Oh, thank you very much, Dr. Javadian. Controversial, I'm sure you know that, bamboo reinforced concrete. I remember a couple decades ago anyway, because it was used very simply, just inserting bamboo culms kind of as a substitute for rebar. But glad to see that you're researching Dendromus asper, an excellent species for any kind of construction use. And I think I'll let Dr. Sastry comment before I pose a couple questions to you. Dr. Sastry?
Yeah, thank you. First of all, Dr. Javadian, 1 second, give me a second to my thing connect today. Okay. Yeah, the iPad is drained. I have to connect to the main line. Dr. Javadian, how did you end up in Singapore?
Oh yeah, I mean that's an interesting question. So I mean, I went to Singapore to study. I'm originally from Iran, but I went to Singapore to study.
Okay, I have 2 questions. When you're reinforcing concrete with the bamboo, you have used different shapes of those strips of bamboo. Does it make any difference? One. The second is species, different species, does it make any difference?
Yeah, I mean, these are all really fantastic questions, and each of them could be a PhD thesis, I think. But to answer this short, yes, the shape makes a difference in bonding. That's why we tested different shapes, and that was very interesting because the shape of the bamboo reinforcement, how we can make it, wave it or weave it, that also makes a difference, and we realized that during our test. But of course, I mean, your second question was, sorry, I missed your second question.
Different species.
Yeah, species. Yeah, I mean, as I said, we only tested Dendrocalamus asper because that was one of the most common species in Southeast Asia. And I'm sure if we have different species with different mechanical properties, then the final engineered bamboo or the BVL could have different mechanical properties. So we can have different bending capacity, we can have different tensile capacity, and definitely different shear capacity. So I believe Guadua bamboo could be even a better choice for such applications, because Guadua, based on some tests that we have done, Guadua angustifolia, so has much higher bending capacity compared to Dendrocalamus asper. But we were doing research in Singapore, funded by Singaporeans, so we could not do something very far from us. But now we are Europe, we are trying to use Guadua and to see how we can use Guadua in similar processes.
Okay.
Thank you. Yeah, thank you very much. I think we need to move on. There's
Thank you so much.
There's several questions for you, Dr. Javadian, and we'd like to pose these during the panel discussion.
Absolutely.
Are you available to stay for the panel?
Yes, I will stay on.
Okay, great, because there's several comments and we want to continue that conversation. But let's get back to Dr. Yuan. Is he with us now? Dave, can you put up Dongchen Yuan's presentation from Nanjing Forestry University?
Dave, apparently you have to allow him to access the video.
Okay.
Yeah, I asked him to unmute. When he came in, I hadn't turned off his video.
Okay, he's unmuted now.
Yeah. Dr. Huang, can you speak? Can you say something? Yeah, we probably still couldn't hear from him, so that's unfortunate. So there's some problem from his end. Then he can show screen, I guess. Is it?
Yeah, he might need to select a separate audio and video on his Zoom.
Yeah. Okay. Can we try Mattia?
I'm not sure. Yeah. So our last speaker of the day is Matteo Gutierrez, who's actually in Tasmania. So it's very, very early in his morning.
No, he's here.
Oh, he's here. Excellent. Yeah. Okay. Well, so Matteo Gutierrez is CLTP Tasmania, and his presentation today is very important: fire performance of engineered bamboo. While he's hooking up, I'll read you a little bio. With a PhD in structural and fire safety engineering from the University of Queensland, Matteo's main research interests are mechanical properties, fire performance, and timber and bamboo design. Matteo has been working on timber and bamboo's mechanical and physical properties as a load-bearing material since 2010. He's one of the founding members of the SIB Guadua Research Network. He is also a member of the Bamboo Construction Task Force coordinated by IMBAR, and the nominated expert by Standards Australia to participate in the working group on structural bamboo in the ISO Technical Committee 165 for timber structures. Matteo joined CLTP Tasmania, CUSP, in 2020, and since then he has led the development of a range of structural engineered wood products such as CLT and GLT made out of plantation hardwoods available in Tasmania. His work has allowed these products to achieve high quality manufacturing performance and certification. And we welcome Matteo today. Thank you very much. Do we have Dave? Could you turn off the video for Dr. Jen? Okay, Matteo. Hello. You've got 20 minutes.
Can you guys hear me?
Yeah, I can hear you. Just need your screen share to rock.
That's good. Well, good morning, everyone. Good morning, Susan. And thanks again for having me here today. As you just said, Susan, it's quite early in the morning for me. So I hope that I don't fall asleep. Yeah, as you said, well, today I'm going to talk about fire performance of engineered bamboo, which is part of the work that I did during my PhD at the University of Queensland here in Australia. I'm going to start sharing my screen. You guys let me know if you can see the presentation, okay?
Looks like it's coming up. Yeah, I can see your desktop.
Thank you. I'm just gonna optimize for videos because I have a video.
There we go. Full screen. Looks good.
All right,
You can
excellent.
see your Zoom bar though. You can drag that over the other screen. You just grab a space and you can drag it over.
Is it better now?
Yeah, there we go.
Okay, excellent. Cool. So again, I'm currently working as a technical development manager at CLTP Tasmania, or COSP. I'm a member of the Inbar Bamboo Construction Task Force and the expert for Standards Australia on the working group of bamboo structures in the ISO committee, and a founder member of the CIP-WADWA Research Network, which is an international research network working in Latin America. My presentation is about fire performance of engineered bamboo. Before I start talking about my work with fire and bamboo, I just wanted to explain or tell you that as many of you, I started working with brown bamboo back in Colombia more than 10 years ago. I did my master's on the tensile strength of the effects of moisture content on the tensile strength of bamboo. And then I did several designs and work with engineers and architects building bamboo constructions, doing research on different universities, and working with the standardizations committee to create the first standards and building codes for bamboo in Colombia. But back in 2016, I moved to Australia to start my PhD with bamboo, and we saw the possibility of working with fire, bamboo and fire, because we knew that there was almost nothing or very little done at that time on fire and bamboo. But the other thing that we found quite interesting, it was exploring engineered bamboo because we believe that engineered bamboo had way more potential on developed countries like Australia or European countries or even the UK. So this is something that you probably already know and you have already seen from yesterday, from other presentations and other days, or even from today. This is the process to make one of the engineered bamboo products that you can find in the market, which is laminated bamboo. So I'm probably not going to talk about this too much, but what you can see on the right-hand side is a cross-section of laminated bamboo product made out of bamboo mussel or Philostachys pubescens, which is the main bamboo currently used for engineered products because it's the main species in China. And the use that they use to make these laminated bamboo is phenol formaldehyde polymer. But what are the advantages of using engineered bamboo products? Obviously, all the environmental credentials that you are pretty familiar with. It's usually a more dimensional, stable product. You can have regular and standardized cross section, which makes like a huge difference compared with round bamboo, that it's always irregular. It's never, you're never gonna have two pieces with the same cross section. So it definitely facilitate the construction of connections or joints, for example. But also it facilitates the use of other machinery, like for example, robot drives or CNC machines to use digital fabrications and things like that. And you can build larger cross sections and with higher load bearing capacity, so you can cover larger stands, you can withstand higher loads, because now you are not limited by the size of your cone, but you are now limited by the equipment and the machinery that you can use in the manufacturing plants. So you can build as big as you want, as far as you have the capacity to make such a product. The homogenization, which is key when you have engineered products, you definitely going to have lower variation in the mechanical and physical properties, because you are now in control of your production and you can tweak things to achieve whatever you want, which is usually something that is very hard to control with natural product. You can build safer, faster and cleaner constructions. And one of the things that was key for us is that you can achieve higher fire resistance, because now you can have bigger cross sections. And usually when you have fire, you're going to have sacrificial layers. You're going to start burning part of that cross section, and being able to have a larger cross section, it's going to give you a better fire resistance. And we will talk about that later. So there are several examples where we can use engineered bamboo, but I just decided to take this one because you can see that with laminated bamboo, there is more potential for using it in urban environments. There has been a lot of construction already done in on the countryside, where you have like rural constructions where the building code requirements are not that high, or where you are not surrounded by other structures. But in a urban environment, the conditions are different. Laminated bamboo has the potential to be used in those applications, but also has the potential to be used in mid-rise or even high-rise construction because of the way that we can build with it. But of course, when we place bamboo structures in a place like that, in a city, in a highly populated area, fire becomes a huge risk, because bamboo, as many other construction materials, particularly natural bio-based materials, is a combustible material, and it can catch fire at any time. So you can see on the two photos on the left-hand side that round bamboo structure caught fire during the construction. This is something that a friend of mine in Mexico, Veronica, shared with me a couple of years ago, and it's a structure in Mexico that caught fire while they were welding the connections. And on the right-hand side, you see a photo of actually it used to be an engineering bamboo product factory that caught fire in Bali. That's a photo from Arif. And you can see here, let me see if I can use the pointer. You can see here this concrete column, and this is what was left after the fire. You can see the same concrete column here, and pretty much everything was burned down. Another famous incident is what happened in Europe in 2020 at the Mosul Waterhouse in the Netherlands, where you can see a massive fire that destroyed the waterhouse next to the main building, and they were pretty much storage in all engineered bamboo products. So It's again a material that is susceptible to fire, and of course, because of the potential of using bamboo in high and mid-rise structures, and because the potential to use it in urban environments more often, we need to start designing for fire-safe structures. We need to design with the same confidence that we use other construction materials. And we need to understand many of the properties of bamboo. We need to understand the flammability, the flame spread, the heat transfer phenomenon, the structural performance, and we need a methodology to design performance-based design solutions. So when we have a fire, fire safety engineers, they have usually divide this problem in two stages or in two different time frames. The first one is when we require to evacuate everyone in the building and make sure that we can preserve people's life. So during that stage, we care about evacuation. We care about understanding how the material catch fire. We want to understand how is the fire growth, how's the material flammability, how the ignition occurs, and how these can lead to the flashover. So that's one part of this problem. And the next part will be understanding the structural integrity, because after everyone has evacuated the building, we want to make sure that the building is not going to collapse and that the fire brigade can attend the fire event and can control that fire. And if the fire brigade wants to go into the building, they can be safe, the building is not going to collapse, and therefore you're not going to be affecting other surrounding structures. So you can divide the problem in two stages. So when I started my PhD, we had a group of 3 PhDs, and what we did is that we divided the problem in 3. Dr. Angela Solarte, she was focused on that first part of life safety, and she did a lot of work on fire performance, ignition, thermal properties, flammability, flame spread, and self-extinction. And she was more focused on the life safety side of that problem. All the way up to understanding the structural integrity, which is the part that I ended up doing. And then we have Dr. Ian Pope, where he put more effort into understanding the heat transfer phenomena. So, and also trying to connect and trying to link both the early stages of the fire with the fully developed fire, or even the decay of the fire, where the structure will be more affected. So again, we were trying to develop a performance-based design methodology where we divided the fire in 3 different stages: a growth phase, a fully developed phase, and a decay phase. Which each stage will have different properties and different things that we analyze. But we try to understand what will be the inputs of that design methodology, and then what will be the failure modes to see how can we design safe bamboo structures. So again, there are many things that can be affecting that process, like for example, the type of adhesive that you have, the thermal properties of the material that we are using. In this case, laminated bamboo, made out of bamboo moso. The effect of the lamella orientation could be very critical as well. Bamboo will behave very different depending on the direction that it's exposed to fire. And then obviously within the properties of the material, you will have the mechanical, like the effect of fire in the mechanical properties of the material as well. And then again, I was more focused into the structural part of the issue. So just moving into those tests that I did to understand the structural fiber performance, I start doing testing on the compressive strength of laminated bamboo. What you can see here is a stress strain curve. The black line, it's like the typical behavior of laminated bamboo. I ended up using the European standard for testing timber, like engineered timber products. So the columns that I use or the specimens that I use were slightly larger. But what we saw is that as far as we start increasing the temperature, you will have a decrease on the compressive strain of bamboo, but also we observe changes on the failure modes. And we move from having pure crushing failures into having larger deformations, and then bamboo start pretty much buckling when the temperatures were above 160 degrees. We did a lot of tests on tension as well, trying to understand the effects of temperature in the tensile strength of the material. We use a heating blanket. We use, in this case, bamboo strips because it was easier to make the test. And because we also, when we did compression, we also did round bamboo test and laminated bamboo test. So at the beginning of my research, I was working with both materials, with round and laminated bamboo. But we very quickly realized that if we wanted to understand fiber performance and if we wanted to do tests at a larger scale, round bamboo was not going to have a very high resistance. So we decided to focus more on laminated bamboo. But what you see here is that there wasn't any changes on the failure modes, but there was definitely a significant reduction in the strength of the material. We did test at a smaller scale on what is called DMA test, which is a very small scale bending test to avoid heat transfer issues because of the size of the samples. And with the DMA, what you do is that you measure the reduction in the modulus of elasticity. So what you see here is a normalized modulus of elasticity against temperature again. And what you see is that there is decrease in the modulus of elasticity, but after 150 degrees, the slope of that curve drastically change, and then you see a significant drop in the modulus of elasticity, where after 230, 240 degrees, the stiffness was completely gone. And then what you can see here that I did is that I compare the results at the bench scale test, because I measure the modulus of elasticity in both the compressive and the tensile strength test against the DMA results. And you can see a really good fit of the bench scale test and the DMA results. So with all that information, we ended up building a reduction factor for temperature, for the effects of temperature. So this is the normalized property. So it could be normalized compressive strength, or the normalized compressive tensile strength, or the modulus of elasticity. So in this case, this is the change in the compressive strength. This is the reduction of the tensile strength. And here with the dashed line, you see the reduction in the modulus of elasticity. And here you have the equations to quantify that reduction factor as a function of temperature. So yeah, you can clearly see here that below 100 degrees, the loss in the compressive strength is huge, which is quite similar to what you have in timber, maybe a little bit a higher reduction, but there is less effect on the tensile strength. below 100 degrees in compression, you start kind of softening the fibers, but after 100 degrees, there is a section where there is no much change because you're losing a lot of, you're losing all the moisture content, and you can even increase the strain after this point slightly. But then after 150, which is where we found that bamboo starts to paralyze, the decrease is huge. And then after 250, we found that the material strength was practically lost. So it was hard to make tests after that temperature, above that temperature, because the samples were pretty much all char and really, really hard to test. So that's why we decided that after 250, we wouldn't use the material at all. You can see more about this on a paper that I published in 2020. So yeah, I've been leaving the links and the name of the papers that we have already published. So if you want to go and see more detail, you can definitely work with those numbers. So with that information, we built some constitutive stress strain models. And with those models, and after understanding the properties of the material, we moved to full-scale testing. So we conducted a 4-point bending test because that was the easiest test to make. We defined one thermal exposure, and then we applied 3 different stress levels. 54% of the failure mode, 40% of the failure load, and 27% of the failure load. This is a video that we took during the test. Again, it's a bending test. The main difference is that we ended up pushing the beam upwards. Normally on a bending test, you do it pushing the beam downwards. But in this case, we did it the other way around because it was easier to control the fire exposure. And it was also easier to protect all the sensors that we had to use. This is not an easy test. We couldn't make it at the structures lab at the university because all the challenges that fire brings with. So we did it at the fire lab, and I ended up designing a machine that allows us to do this test. And what you see here is that I painted the surface of my bamboo sample to be able to use a digital image correlation analysis. And this is a video that shows how we applied the load, we bended the specimen. Specimen was subjected to a constant load, and then we start burning the element until we reach the fire. So again, if I repeat this video, you can see that we again bend the sample until the stress level that we define. We left it at that constant load. Then we start burning the sample, and you can see with this digital image correlation that you can pretty much track the areas where the material is going to fail. We measure deflections and we measure strain with that method, but we also use contact sensors to do that. We use strain pods and we use strain gauges. The problem is that the strain gauges were lost very quickly. So with that test and also other tests developed by Ian, we calculated charring rates. The charring rates help us to develop the heat transfer models. You can see here charring rate against time. And also because charring rate has been a very commonly used property to understand timber performance. So, yeah, and it's definitely, it was definitely key for us to develop the heat transfer models. You can see that the charring rates changes with the different fire exposures and also changes over time. This is particularly important in materials where you don't see char fall off because of the type of glue that we use in laminated bamboo products. We didn't see and we didn't experience much char fall off, which is a very critical situation in timber. Again, with that information, we calculated the temperature profiles. And with the temperature profiles and the constitutive stress strain models, I developed a method to calculate the structural capacity. And what you see here is that in purple, you see the experimental results of those tests, where I have the failure load on the y-axis, and on the x-axis, I have the time of exposure. So you can see how the material start losing capacity over time. And in red, you see the model that I developed, and in purple, you see the results of the experimental test. And what we observe is that the model and the experimental results have a really good fit. So we were very happy with the methodology that we developed to predict the capacity of those elements. So in conclusion, we understood and we investigated the reduction of the compressive strength, tensile strength as a function of temperature, and we developed those reduction factor equations and charts that you can use in future bamboo projects exposed to fire. We study the bending capacity, and we realized that with the stress strain constitutive models at elevated temperatures, you can calculate the capacity, but you definitely need heat transfer models and stress strain models. For the future work, I feel that we still have a lot of knowledge gaps, and if we want to include fire performance in future standards, we still have a lot of things that we need to better understand. So there is a risk that future standards, because of that lack of knowledge, are still going to have a lot of prohibitions. We are going to incur in higher risk. I will definitely recommend that for future projects, we need to investigate bigger scales and start doing more full-scale testing. These photos are taken from some tests that we recently did at COSP, a company that I'm working with, on plantation hardwood CLTs. And these full-scale tests can be furnace tests, but we also need to do a lot of non-standard tests. We need more compartment fires. We need more real fire type of tests that allow us to have a better understanding of the behavior of full-scale elements. So that was it from me. And again, thank you very much for having me here today. Here are my email, and I'm happy to take any questions. Thank you.
Excellent. Thank you. Thank you, Mateo. It was really amazing. We have a lot of questions for you. I just want to make a note to the audience that we're going to try to bring back Professor Dongsheng Wang's presentation, but let me just give a couple questions to Mateo. From the audience, Dr. Sonar asked, is the first 10 to 15 minutes duration of fire is important for the safety?
Is important for what, sorry?
He's asking if the first 10 to 15 minutes are the most important for safety. I'm not sure exactly what.
Yeah, well, again, there are different type of risk and different type of effects during a fire. In the first 15 minutes, where you have the fire growth and where the compartments had not reached flashover yet, they're very, very important for people's evacuation. If you are in a low-rise building, if you are in a single-story house, people will evacuate very quickly. And yes, the first 15 minutes are definitely critical. If you don't have them out of the house or out of the structure, then you're going to have a problem. But if you are in a 20-story building, and I know that we haven't done 20-story bamboo buildings yet, but we have definitely done it in timber. If you are in a 20-story building, people probably won't be able to evacuate in those first 15 minutes. And that's when the fully developed stages of the fire are so relevant, because there will be many cases where people cannot evacuate the building because of the conditions that they are at, or because of the fire strategy that you have used. And in those cases is when you need to guarantee the structural integrity of a building. And then the late stages of the fire, became critical. And that's why you have to understand the whole fire duration and the effects on the fire on the properties of the material, even after those 15 minutes.
Okay. Also, question, is bamboo charring rate different than wood?
Yes, it is.
Okay. And another important question about the thermally resistant adhesives for laminated bamboo. So there are several questions about the adhesives and how they might be affecting the flammability.
That's definitely critical. Adhesives are definitely critical. And when we have engineered bamboo, it's a completely different ball game, because in round bamboo, there is no adhesive. And it's the same concept for timber engineered wood products. The performance of the engineered product, it's now not only depending on the raw material, but of the type of adhesive and resins and things that you use to make it. Again, as I mentioned before, most of the engineered bamboo products, I will say, at least all the products coming from China, they laminated bamboo particularly. I know bamboo screen bear is different, but for laminated bamboo, most of the products are made out of phenyl resorcinol formaldehyde, and phenyl resorcinol formaldehyde has a really good performance at high temperature. Problem with phenyl resorcinol formaldehyde is that many countries are not allowed to use it, or they have a lot of restrictions during manufacturing. So, and that's one of the cases in Australia. But phenyl formaldehydes are better adhesives for high temperature. If you work with polymers, with polyurethanes, polyurethanes are thermoplastic materials that will react to temperature at quite low temperatures. So you definitely start losing the bonding properties at quite relatively low temperature. So yes, the type of adhesive is critical for the performance of the product.
Well, then I think the answer is rather obvious for Anthony's question, but I'm going to pose it to you anyway, because it is something of concern. The only good quality construction bamboo he can get in Haiti and the Dominican Republic is treated with diesel. How worried should he be?
Well, yeah.
Yeah, that's not a good treatment method, I assume.
Well, not for fire. You know,
Yeah.
like again, when you are doing a engineered bamboo design, you always need to take a holistic approach, and also define what are your higher risk. I imagine that he's using diesel because of the durability and because diesel has proven to be effective for insect attack and things like that. It's a very common method used in Colombia. And I can remember the famous architect Simon Vélez that says that he loves to put very toxic substances on bamboo, and diesel is one of them. But yeah, again, what are your risks? If people have found it effective for durability, well, I don't know. It's not my area of expertise, but for fire, diesel is a combustible product, and if you're putting a combustible product on a combustible material, well, the only answer that you're going to have is that the material is going to catch fire.
Yeah. Okay. Thank you. We've got several other questions for you, but we're going to try to bring back. I'm sorry, Dr. Sastry, my colleague. Do you have a comment from Mateo?
Yeah. You covered a lot. Matteo, very well done. Two questions. I like the way you address it, life safety and structural integrity. That's the way to look at it. But what were the fire retardant chemicals you tested? Does it make any difference?
I didn't test any fire retardants during my research, but the main difference that you will have with fire retardants is that you are going to delay the fire growth. And that obviously going to have an impact on the life safety design. If your material is not going to catch fire that quickly, you obviously going to have a little bit more time for people to evacuate and egress the buildings. But in a late stages of the fire retardants are not going to have much effect unless that they probably reduce the charring rates. But yeah, there are other methods to treat or to protect
So does it
bamboo.
make any difference?
That's
Does it
yeah,
make
that's
any-
what I'm.
the type of retardant you're using?
Again, I didn't test it, so I don't know if there is any difference between different retardants. But what I'm telling you is that there is a difference if you have bamboo without treatments or bamboo without protective coatings or
They
protective.
kind of fire, there are a dozen or so or even more fire retardants, depending on what you're using. Does it make any difference? Ask you or some others, like diesel, like what Suzanne is saying, which is not a fire retardant. The chemical you're using for fire retardant treatment of bamboo, does it make any difference? What kind of the product you tested, what kind of fire retardant treatment did you use? Chemical, the name of the chemical.
No,
That's what I'm
he's actually saying that he has not tested any of the fire retardant materials. He's just testing the engineered bamboo per se.
Treated.
Untreated.
Untreated.
Untreated for fire protection, yes.
Oh, okay.
untreated for durability and untreated for fire protection. Nothing that I tested had any type of treatment. It was all raw material.
All right, okay. Thank you.
No worries.
Okay. Thank you, Mateo. Excellent. Can you
No
stay
worries.
on? Can you stay on, or do you have to go back to sleep?
No, I'm gonna stay until we finish the.
Okay, we have more questions for you. All right.
Thank you.
Can you hear us?
Hello,
Dr.
can you hear me?
Wong?
Okay, please let me know. I open the camera. Can you hear me?
Dave, can you help with the camera?
Yes.
Yeah, I just
you
sent the
can.
request
Yeah.
to turn on.
Yeah.
There we go.
Thank you.
Okay, can you hear me? Hi.
Yes.
Hi.
You should be able to
Hello.
share now also. Seems when he tries to share, we've lost his camera and audio now.
Yeah.
Maybe it's just taking a while to render. Susan, you're muted. There
Yeah,
she is.
it must be a bandwidth problem or something.
I believe I have his presentation, so I could probably run his presentation.
No.
No, but I'm wondering if you ran the presentation, and he turned off his video, maybe he could verbally go through his slides.
Well, it seems every time he tries to share his slides, we lose his camera and his audio.
Yeah. Why don't you turn? Yeah, you turn on you share the slides.
Okay,
And
I'm gonna
then
stop his
ask
share
him
and
to
hopefully
just-
he'll come back.
Yeah. Yeah, Professor Huang, don't share it, okay? And Dave is gonna play the PowerPoint. And can you speak?
He's trying to
you-
share again.
Yeah, no, don't share it.
I'm gonna stop
Professor
him again.
Huang, don't share it. And just talk. Can you talk? Okay. Like in view of time, maybe, okay, now we can see it.
That's me sharing.
Yeah, I know, but Professor Huang, can you speak? Yeah, we cannot hear him. So let's just skip this and Suzanne and if you think it's all right, and let's just go right into the panel session. It's unfortunate that we cannot get the technology work for him today.
No, but perhaps when we compile the question and answers, we maybe could include his PowerPoint. But I don't know how else to salvage his presentation. Oh, here he's
trying to share again, but we can't hear him or see him. So
yeah,
as soon as he tried that share, that caused his whole system to crash, I guess.
Yeah.
Unless his microphone is open. Can you hear us?
No, he can't.
Yeah.
Even Professor Huang, can you say something?
I can hear you.
Okay, so let's go.
It's okay.
Yeah, we can see your screen right now. Just roll on. Just talk.
You can speak. You can hear me.
Yes.
Okay. Could you see the
we
sharing?
Can see the slide.
Yeah. So I can begin.
Yes.
Yeah.
Okay. Sure. Okay, I go through quickly because the time is lost. So first I need to talk about why we need to use the engineered bamboo. Fine. So China is the world's largest population. Numerous buildings are needed to accommodate the large populations every. So yeah, so every year trillions square meters of housing and other buildings are constructed. Massive stone, sand, and other non-renewable resources are consumed to make concrete, steel, and other construction materials. So as a consequence, vegetations are destroyed due to large-scale quarrying. So we need to reduce the consumption of mineral resources and to use renewable resources such as wood and bamboo. So actually, China has a long history to use bamboo as a construction material. So housing made with raw bamboo can still be seen in southern China, but there are some problems. So first is their low stiffness or bonded connection cannot fulfill the requirements of modern buildings. The other one is the dimensional diversion of bamboo comes and they're vulnerable to decay. So we use the engineered bamboo. So
Professor Huang, are you turning the page? Are you?
Okay. So as according to the research our team, the engineered bamboo, the strength of the modulus and the modulus are closer to an even better than the wood products. So this table shows the engineered bamboo composite the mechanical properties. So according to our test, so we compared the mechanical properties of engineered bamboo with the wood products. You can see it's almost similar or even higher. So there are great opportunities in China. So in China, around 20 trillion square meters new buildings erect in China every year. So more and more people accept engineered bamboo composite as the construction material in recent couple of years. So here I show you some examples we built in China. So the last one is the concept design of the bridge. So it will be finished this year in Fujian province.
So, Professor Huang, we cannot see, like your slides is not moving.
Okay, now it's moving.
It's not moving.
Yeah, it's moving. So we are moving.
No, your slides aren't changing. I think you may be sharing the wrong screen.
Professor Huang，你的那个 slides，我们这边看到它不动了，还是在第一页。
哇，这我一直在动啊！哎呀 ，I don't know.
Would you like me to share the slides and you can just say next slide?
Yeah.
Okay, I'm going to share your slide deck.
Yeah, Professor Huang.
It's moving now.
Yeah, now it's moving. Yes.
Yeah, now it's changing.
Okay, I use it this way. It's not a play.
Just go
Yeah,
on.
not a play style. Yeah, it's not a play style. Is it moving?
Yes.
But it's not a play style, so
That's
the
okay.
video cannot work.
No,
Okay,
that's okay.
Okay. So we have some challenges. So first is how to make bamboo composites with the stable properties to meet the requirements of construction engineering. The second is the design philosophy of EBC structures. So the last one is economy and acceptability. So the problem is the bamboo products are originally used to make furniture, handiworkers, decorations, flooring, and so on. So the mechanical properties such as strength, MOE, and creep are never be concerned. So there is no technique to control the magnitude of stability of mechanical properties introduced in the manufacturing process of bamboo products. So current manufacturing techniques have many shortcomings. So lower efficiency of mechanical utilization, high labor consumption, unstable quality of the products, and no specific mechanical parameters available. So these shortcomings are the major factor hindering the application of bamboo composite in building constructions. So to resolve these problems, so we must we should need to develop the manufacturing process technique. So this picture shows the pilot line to explore the industrialized process technique for EBC manufacturing. It allows to make EBC panel with thickness up to 400 millimeters, 6 meters long, and 600 millimeters width. So by selecting proper bamboo strips and control the processing pressure, the end products with expected properties, many longitudinal strengths and MOE can be obtained. So the other one, we need to study the constitutive properties of EBC. So this picture shows the stress-strain relationships on the test. So it exhibits significant linearity. So the constitutive linearity and the lower transverse strength makes the response of building, of bending or combined bending and compression members present prolonged nonlinearity in the ultimate state. So to predict the load carrier capacity and deformation of these members in accordance with elastic theory could significantly predict the load carrier capacity of the members. So how to predict the load carrier capacity and ultimate deformation of these members? So this picture shows the test of bending and bending members. Yeah. So we give the modeling we developed a model to predict the load carrier capacity of the bending member. So we compare the results, the prediction results to the test results. So a good agreement can be achieved. Next. So this picture shows the combined bending and compression members. So we developed a model to predict the load carrier capacity of the beam columns. So here we compare the modeling results with the test results. So we also get the good agreement between them. So this picture shows the bio bending and compression. So also developed a model to predict the load carrier capacities and the deformation of the member. So here we compare the test results and the prediction results. So the other challenge is the fracture. So we need to answer the two basic questions. So on what condition will the crack extent and the crack tolerance of the fracture? So this video shows the crack processing of the bending members. So it shows the crack in the middle depth of the bending shearing segment crack along the fibrous direction. So please, so the video doesn't work in this model. I'm sorry. It shows the process of cracking generate and developing in the bending shearing segment. Obviously, the failure mode of EBC is significantly different from that of isotropic materials. That's the shear strength evaluation method must be different from the evaluation of isotropic members. So such as steel concrete members. So on the other hand, like wood members, EBC member may work with initial cracks. These cracks may be generated due to the imperfect gluing and uneven layout of the bamboo strands. So therefore, we must answer the two questions, the basic questions. So EBC fracture presents conspicuous nonlinearity. So in the crack tip front, the evident fracture process zone can be seen. In this zone, many fire cracks are generated and the fiber bridges can be observed. So that the constitutive relationship of the material no longer obey the Hooke's law. So the stress intensity factor cannot be used to measure the fracture property of EBC. So the fracture energy is adopted to measure the fracture property of EBC crack. So we developed a model to calculate the critical fracture energy of mode 2 and mode 1. This picture shows the mode 1. So we use the trilinear, the cohesive model, develop a model to predict the opening deformation, and we predict the load deformation curve and the energy resistance, the curve here. So this picture shows the mode 2, so the shearing in the plane. So we also have a good result compared to the experimental and the model prediction. So sometimes they have the mode 1 plus mode 2 fracture. So this picture shows how to study the the 1+2 hybrid fracture. We also develop a method to get the energy resistance curve for these fractures. So this is the detecting crack length by using DIC and high-speed camera technique. So this, okay, it works. So you can see the crack tip expanded with the loading increase. So here shows the relative displacement of the crack tip. Here is the crack tip. Yeah. So we use this instrument equipment. We can directly get the load and the crack length, which can be used to calculate the energy resistance.
Professor Huang, can you finish in 1 minute?
Okay, I try. So this picture shows me. I go through quickly. So this is the bolter dive types of the connection we developed. We call it energy dispersion joints. So we'll go to the last one. So I show you this picture, this sensing picture. Okay. So this shows the study on the creep and the macroscopic property. So here I show you the microstructure of bamboo cubic. So it shows that the bamboo is the viscous material. The creep is the nature of the bamboo composite. So cell lumens, vascular bundles, and microvidules are scattered in the material. This foam structure allows the water and the air come in and comes out in the material in case the ambient temperature and humidity changes. So therefore, the moisture content and the internal stress may change as the ambient circumstance changes. So this may significantly accelerate the creep of EBC. In other words, the deformation of EBC member is sensitive to the ambient environment change. So there is a problem how to evaluate the long-term structure, long-term behaviors of the EBC structure. So what shall we do next? So in general, engineered bamboo composite is a relatively new building and construction materials. Its mechanical properties are like that of wood products to some extent, but not the same. So what we should do next? I think we need to fill the gap between the bamboo and buildings. So we need to solve the problem how to manufacture bamboo composite having the properties of specific mechanical properties and to meet the requirements of building and construction engineering. So the other one, we need to build the design philosophy based on EBC's nature and to build the standard system for EBC structure design. Okay, thank you. Thank you. Champion.
Thank you.
Thank you. Oh yeah.
Thank you, Dongsheng.
Good.
I understand your technical issues, but now I hear an echo when I speak.
That's Dongsheng's mic picking up your voice through his speakers. You might have to mute while other people are speaking.
Okay. All right. Well,
okay.
But thank you very much. Dr. Sastry, would you like to comment?
Yeah, I missed this first part. But doctor, can you explain a bit more on the mechano-soft-to creep? What do you mean by that?
Sorry, can I repeat the question?
Mechano-soft-to creep. That's what I read in one of your slides. You mentioned that bamboo, moisture and others, come in and go out, and that might result in mechano-soft-to creep. That's something new definition, new term, I didn't follow. In one of the slides, you used that term.
Sorry, it's not clear to hear you. What do you say?
Mechano, MECHANO, SORPTIVE, SORPTIVE, creep. The humidity and moisture change in the product.
I can help a little bit. And so Professor Huang, he is asking. I guess I can just explain a little bit.
Yeah,
Mechano-softive is that
Mechano-softive.
Yeah, mechano-softive, yes.
Yeah. So because the bamboo is the foam structure in the micro scale, so it's if the ambient environment, humidity and the temperature changes, so the pressure will changes. So they will drive the water in the air comes in or comes out of the bamboo. So it will be change the stress state in the bamboo. So the vascular bundles, micro voids can be changed. So this will be, significantly accelerate the creep of bamboo. So
Okay.
Is that clear?
We'll leave it at that. I have to look at it. Okay, thanks.
Okay, thank you very much. It was very interesting, and I agree with you. At the end, your last slide, what do we do next? Yeah, we have to design. We have to kind of change our design philosophy to meet with the engineered bamboo product, and have some standardization in that area. So thank you very much for your contribution. I think we're running late, as I'm sure some of the participants have to go elsewhere and go back to work and whatever. But I'd like to move to the panel discussion. So any of the speakers today could, if they could turn on their cameras and join us for panel discussion that we had allowed about 30 minutes, but I'm not sure. I'm not sure how we'll go, but a few very interesting questions need to be addressed, and I'd like to actually start. I've got questions for all the speakers, but I know that Dr. Harries is anxious to talk about the concrete, bamboo reinforced concrete issue that Dr. Javadian brought up. Well, no, there's some other questions too, but Dr. Harries, I know.
Okay.
I am setting you up because you have opinions you'd like to share.
Oh,
so please.
God, I have, yeah, and on bamboo concrete too. So I think Ali Reza is probably familiar with the paper that we wrote a couple of years ago looking at bamboo reinforced concrete. And for any number of reasons, but the one that I will ask you about is why on earth would we reinforce a brittle material with a brittle material? And I could go on, and I'm sure you're familiar with our paper, and if you're not, I'll be happy to send it to you. And I noticed that Hector was in the audience today as well. He's the lead, Hector Arquia was the lead author on that paper.
Well, I think that's a very, very important question. And I think I totally agree with you that we should not reinforce a brittle material with a brittle material. And what also our research we also did was also we also had the same challenge. So as you know, as any research, we have seen in the past that a lot of people try to replace steel with natural bamboo to reinforce concrete. And that has been a little bit misleading. And a lot of people, especially in Brazil, in Colombia, in India, they have been using natural bamboo as a replacement for steel, which is, beside being brittle, we have a lot of challenge with differential thermal expansion. We have a lot of challenge with debonding. And of course, the problems can go on and on and on, a lot of problems. So we decided to see what would be possible with engineered bamboo, because we see a huge interest in that area. And we thought, okay, that could be an opportunity to explore the research in this area. But I totally agree with you. If we have a better material, if we have a more affordable material, and especially for this region, so it's still a reinforced BVL or engineered bamboo reinforcement are not made for Germany, are not made for Canada, are not made for Singapore. They are made for really very affordable homes, like 1 stories, 2 stories, no earthquake zones, people who cannot afford it, they want to build something fast, prefabs, and cheaper. And again, I totally agree with you. If we have a better options, we should not do this. We also do not recommend this. We also had a couple of papers on that we have shown that there is a very limited number of areas that we can use really engineered bamboo as a reinforcement for concrete. And that was the reason that when we moved to Germany, we started to work on a little bit other species to see if we can make the elastic modulus higher or not. So far, not possible, but still our research are continuing on the 3D printing and digital fabrication with ETH in Zurich, and we see how we can improve. So how we can use even low mechanical properties through geometrical design, through bionic design.
So you do have a model for doing this in glass fiber reinforced concrete. And so I was very curious to see that you were comparing your data to ACI 318 predictions, where it really should be compared to ACI 440 predictions. When we design with glass fiber bars, which are brittle, so I'm reinforcing a brittle material with a brittle material, we fundamentally change the limit state. Concrete compression is now my dominant limit state, which changes the dimensions of the member and actually would offset any sustainability that I might get by replacing, and I hate using the term replacing because that's not right, steel with bamboo, but we do have the model. So when you're looking at predicting these things, go to ACI 440, go to the new Eurocode 3 provisions, which I think are available for FRP now. Don't go to 318. Don't compare it directly with steel because it doesn't make sense. And I mean, the US Navy showed this in the 50s, that it doesn't make any sense. The 40s.
Actually, our design, all of design was done according to ACI 440. So the green columns that I showed to you and the red ones is all based on ACI 440.
Oh, okay. I'm sorry. I thought I saw.
Yeah, no, that's fine, because I think this was my mistake. I didn't highlight that in the graph that is not ACI 318, because as you said correctly, it does not make any sense. Okay. Yeah, but generally I agree with you. I have read your paper, I have read your criticism of using this, and I totally agree with you. But I think our research, beside the motivation was to see how we can change the ideology that bamboo can be used as a reinforcement, especially natural bamboo. Besides
let's throw this open to everybody else here for a second, because one of the things what can happen with bamboo, or with, grant you it's not a new material, but it's a new material to many, many, many engineers. If we put it forward in something that doesn't work or fails, it's not going to help. It's going to be a poor reputation. We saw this in the early failures with FRP. When something goes wrong, oh, it's the bamboo. So we want to be really careful. If we're going to promote an industry that's based on bamboo, we want successes. And regrettably, failures show up much better than successes do. We all know this by looking at bridge failures or anything else. So I would encourage, I worry about bamboo reinforced concrete, and I think everybody knows that, so I'm going to stop. But how it can affect other aspects of a bamboo related construction industry has to be considered as well.
Suzanne, you have to turn on your mic.
Oh, thank you. Kent, thank you very much. Does any of the other speakers want to speak to bamboo reinforced concrete? I do have a couple other questions from the audience. Okay, I've got a question here that can any speaker explain bamboo usage in shuttering plywood, concrete formwork? Bamboo strip board with film facing is the most common type of shuttering formwork using bamboo. Dr. Javadian, can you comment on that, or Dr. Harries?
I'm not familiar with that term, unfortunately.
I'm not either.
I am. It's fairly common in Chinese practice. So shuttering is essentially formwork.
Yes.
And the reality is it's a one-off. It's using plywood once and typically throwing it away. And so often it's a much lower quality product, almost like a woven product that's got a lot of resin in it. They'll do a resin-rich layer, hopefully to give a nice, assuming they put the resin-rich layer up against the concrete rather than on the outside. And so it's a very inexpensive product and typically intended for one use. You might strip a beam and use it twice or something like that. You know, it has its place. If we're going to continue using concrete the way we do, we need to be able to form it up. And certainly the lower quality product as compared to even a plywood or something is useful. It's not exactly the nicest product in terms of the way it's fabricated. I've been in a couple plants where they're making it and it's not pleasant, but
Okay,
that's another issue.
Yeah, both of these questions came from India. And thank you for the questions. Tomorrow, Dr. Mahanti is going to be speaking, and he's from IPIRT in India. I'm sure he can address this issue because it is very common practice in India to use this type of shuttering. So I'll leave it at that. Let's see. Okay, for Kent, one more question for you, please. We've got a question. Would bamboo scrimber produced with a biodegradable resin be the dream product that can replace conventional timber?
It would certainly be a nice product. I think we always have to be careful with using terms like replace and whatnot. And the minute you say replace, you're going to anger a bunch of the wood guys. Mm-hmm. So we got to be a little bit careful with that. There's no question of bio scrimbers or bio-based scrimbers. Yeah, that would be good. There are people working on them. I don't know how far along they are, and I don't know if there's anybody in this call familiar with it, but absolutely.
We're working on a project with a Dutch architect at the moment, which is looking at exactly that. And Ken, I agree entirely. Replacing, no, it's complementary. And it's got to be seen as complementary. And it's the point I was making. They are entirely different properties. I mean, they work in different ways, and we need to treat them as that. And I think it's very important to understand that. Replacing, no, it doesn't replace timber.
Good.
And I think, interestingly, you know, when we start to develop when bamboo, engineered bamboo, becomes more acceptable, code approved, all these things, which is kind of beginning, then I think you will begin to see not only composites of bamboo, but composites of timber bamboo, but actually materials used together, timber and bamboo, where they use the most appropriate properties, and you use the material that's appropriate for that specific condition. Yeah, which I think is what's very exciting.
Yeah, absolutely, Neil. I agree with you. We have another question directed to you, so I'm glad you're here. What are benefits and limitations of 3D printing in bamboo design and construction? Can you speak to that?
I mean, you know, sorry?
Yeah, can you speak to that?
I mean, the thing is, as I said earlier, one of the most fundamental things is the connection of timber or bamboo, natural materials. It's kind of generally connections become the kind of real big deal because of the transfer of forces through natural materials. And I think 3D printing and trying to show the connection detail we were talking about. I mean, we've been talking to David Trujillo about a different connection detail. And I know with the various groups around the world looking at ways of connecting natural materials together, 3D printing is definitely, we've been working with the people in Italy, whose name I can't remember for a second, 3D printing people, about developing connection types using 3D printing. I mean, you know, I think 3D printing for testing, prototyping, sampling is good. I think for mass kind of stuff, it's a different technique. But I think as to understand and look at the way, you know, the connections and details work, definitely. No, I don't know about 3D printing. Do you mean 3D printing the bamboo itself? Taking the bamboo?
I'm not sure. This question came from Dulce.
I think it's more to do with connectors.
Sorry?
More to do with the connectors.
Okay.
Yeah, but people always describe bamboo as vegetable steel.
Mm-hmm.
And we say it's vegetable carbon fiber, because you can lay fibers up you're taking the kind of advantage of the strength of the vascular bundles and lay bamboo fibers up just like carbon fiber. And so putting the strengths where you need the strengths. And I know that bamboo is now used in the production of aerogenerator blades, which is pretty amazing, because it's a lot. It's kind of the strengths and properties of it are perfect.
Right, right. Speaking of strengths, someone did ask if you could put your slide up again. The slide.
Kate, I saw. Kate, I will take it.
Strength comparisons. Yeah. Right? The strength comparison slide. Can Neil put that up again? I don't know how complicated that is for you to pull that up.
Why
I can share that for you if you tell me which slide number it is.
Which slide it is? It's slide. I can tell you exactly.
There's a table. There's a table.
Slide 37.
37. All right, I'll have it up for you in just a sec.
Okay, that question's for
Thank
Kate.
you, Dave.
That came from Kate. So we want to make sure Kate gets answered. Okay.
I just want to.
And there was a question. There's a question about the different treatments for fire, and the whole building at the British Pavilion. We had to go through a whole series of different proposals for treatments to get it to work and under fire conditions, because in Dubai, you have to go through the Ministry of Defense to get approval. There's a second layer approval. And so it makes a huge difference what retardants you use. Yes, Kate, what was the question?
That was it. She was asking about she was wanting that.
Sorry, I'm just fielding selected questions from the sea of questions in the chat. That was one of my tasks. So I don't know who it was that originally asked for the table. They just wanted a...
Oh.
Okay.
I mean, the Moso bamboo infinity stuff is slightly out of date. The Lambu, the GLC 24C is good. Baobook's good. And the RenewTech is the latest. No, there's a slightly later version of the Verilam stuff, because it's now called Radlam, and they've slightly altered it. So it might be a slightly old table, but the principle remains the same. And I think actually some various kind of speakers this afternoon have shown me I've seen even more amazing properties. It really is absolutely remarkable.
That radial laminating technique looks like it's really revolutionized engineered bamboo in terms of the recovery and also salvaging the fibre-rich outer part, which is normally cut off and lost.
The denser bundles.
Yeah.
I mean, I don't know if anybody's. I hope nobody's on. We've asked for verification, proof of testing from them, and we've yet to receive it. I mean, it's published data by them on their website, but we have been looking into it because we're looking into a project in the USA at the moment in Atlanta. So we're trying to see if we can't adopt the use of it, but we need, proof, evidence of the information to be able to provide to the authorities.
Can you hear me?
Yes.
Yes.
Is that Matteo?
Yeah, this is Matteo. Hi, Neil. How are you? Sorry, I missed your presentation. It was at 2 a.m. for me.
It's okay. It's nice to see
you. Yeah, nice to see you too. I'm not familiar with the RenewTech Verilam, but I'm very surprised by that tensile strength value reported on that table. I mean, considering that we have an engineered product where you need to do joints, you know, like in timber, we have usually finger joints or butt joints, and in laminated bamboo, you will have something similar because of the length of your fibers. I'm very curious, how did they get to 150 megapascals of tensile strength?
Matteo, after this, I'll send you the data from their website and you can take a look. I mean, it is, like I said, it is published data by them, but like, as I said, we've had no, I mean,
But
do you know?
But as we all know, we can publish any data that we want, and it's nice when, you know, Matteo, good engineering eyes. I can't make a composite material of multiple pieces that's stronger than my original material. I mean, the physics doesn't work.
Okay.
So we need to look at these things with that eye as well.
Yeah, Ken, of course you're right.
Yeah, it's very high, definitely very high. Really hard to achieve such a high value in a composite material.
Can we stop sharing the screen, maybe?
Yeah, actually, there's a few questions for you, Changping. If everyone will allow a few more moments. Some of these are very quick. Changping, what was the resin used for the bamboo pipes, the winding pipes in China? What resin is used?
They use modified UF resin.
Okay.
And yeah.
Another question was 6 days or so for drying is quite long. Do you know of any solutions of speeding up the drying process?
Yeah, we're working with the mills, and first off, the kiln, the drying, when it comes to drying control, there's almost none. So so there's lots of improvement you can make by controlling humidity and temperature and program it.
Okay.
And so the kiln itself has to be improved. And yeah.
Yeah, there's another question regarding sourcing. How does this relate to what's manufactured? For example, strand woven products allow us to use higher percentages of the comb. But what about sourcing? How is that affecting manufacturing?
The sourcing, and obviously, well, different species will be different. And I don't know if I understand the question properly, but the goal here is, you know, like is you make the lamina and first, and then it's all about sourcing. You know, like the best way it looks to me is to make the lamina first close to the source, you know, close to the bamboo forest, because you don't have a lot of time to transport the bamboo comb like we do with wood. Yes. And also you have to process it very quickly, and so there's not much to pile up in the yard. So you have to be very close to the source. Yeah. Once you go through that treatment and drying process, and even a bit of a pre-manufacturing into a lamina, and that lamina can be effectively transported and can be laminated, let's say, with wood or with other, you can do some shaping in the next phase of a construction manufacturing, right? So I think, you know, the best way to make it work for bamboo or hybrid bamboo product is have this, what I call a satellite manufacturing model. Right, and I'm a strong believer in using what's local. You know, many people around the world see the Moso, you know, the magnificent resource development in China because of the large Moso forests. However, Moso is very specific on where it grows, and so thinking that you can develop use that as a model in other countries is rather unreasonable, because Moso is a very difficult Philostachys to grow. So I actually am very much a proponent of using what's local, and I think a lot of these things we'll learn as this research continues. Species does matter, but utilizing local species makes a lot of sense. And in some cases, those local species, they haven't been studied. So we've got a lot of research ahead of us. I think here we are at almost I have one final comment.
Yes, please.
If I may, just a very quick
Sure.
regarding to the earlier question about the scrimber being the ideal building material for bamboo if it's mixed with glued with biodegradable glue. And I like Ken is not a big fan of concrete, bamboo reinforced concrete, and I'm not actually a big fan of a scrimber because the way it's being produced now, and it's okay to use for floor, but it's not a good structure or the manufacturing process strategy to make it into the building material. So there's lots of work to be done there.
Just one question. Hello?
Yes. Yeah, we can hear you.
Yes, go ahead, Sherlock.
I'm so surprised that nobody's talking about bamboo plywood or bamboo mat board, those big boards, you know. When you talk about construction, it's not always the big beams, but these are more common and can be used much wider and easy to introduce. Not much engineering is required. No, already the technology is known. Any comments on that from the experts here?
Anybody? I have some comments, but I want to give that to other people.
I suspect that Dr. Mohanty will bring that up tomorrow, being a lot of his research has been in that capacity. But Dr. Harris, do you have any comments on the woven mat board, et cetera, in construction use?
No, I mean, keep in mind that as a structural engineer, I'm thinking about load-bearing applications, and I'm not seeing a great deal
right
in the load-bearing side of things. And
okay, okay, fair enough.
Yeah, we're doing quite a bit of work on the panel side, Sarah, and
I see a lot more potential now in the housing here.
Yeah, we're very interested in combining that with the good old Douglas fir or spruce veneer. So there's a better make optimum use of both resources.
Right. Well, I mean, today we really touched on a lot of excellent research, and I thank the speakers for that, and I thank the audience for all the good questions and the participation. Sorry about a few little technical glitches, but we got through it and we've gone over time, but we appreciate everybody. I think what some of the things that we've learned is, well, I think we've shed I think there's this overwhelming feeling about, yes, we're not trying to replace anything. We're just trying to add something that brings a lot of side benefits along with it, and a material that's been underused and underutilized by the masses. Well, I shouldn't say the masses, because I mean, bamboo constructions have been going on for a long time, and people continue to build bamboo houses, and they always will if they're living near it and it's right there and that's all they can do. But we have a great potential to improve upon that, and that's the point of this conference. So tomorrow we've got some exciting speakers. Again, we've got another 6 speakers talking about their research and the more potentials of engineered bamboo products and engineered bamboo in construction, and helping us with better sustainable building methods around the world. So Chungping, if you have any final words from the UBC side, or Dr. Sastry, if you'd like to say a couple words, I will hand it over and just say thank you again to everyone.
I think it was a really excellent second day we had, and I must thank everybody. Each is a gem, and I should say kudos and congratulations to the authors and innovative ideas, and it augurs well for bamboo. As we didn't have time to discuss how to market this in North America and what type of competition we'll face from the timber people. and how do we promote more bamboo plantations, in North America, So, there are, I think the future, as I see it, it's good. I see good, potential for bamboo. Not to replace timber completely, but at least to add on to what we have to save at least some of the forests, from destruction. Okay, thanks, Susan, and thanks everyone.
Thank you, Dr. Sastry. Chung Ping, final words?
Thank you, everybody. Just one note, we're going to be compiling all the questions, and we're going to be sending out and then follow up with the speakers with relevant questions. Hopefully we can put it all together and make it available. And again, great work with everybody presenting, and thank you very much for attending. We'll see you tomorrow.